In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality.
All right, hello and welcome. This is the curious case of who solved quantum electrodynamics, because the solving of the equations associated with it are, obviously strongly associated with the physical interpretation of it, right? We hear a lot of things about quarks and bosons, fermions, leptons. Leptons change in flavor, upspins, downspin. Who's spinning? Is it me or is it you? Anyway, so we're going to get to the bottom of that and kind of go over the mathematical history of it and kind of the broader concepts of what it is. Because when you go to YouTube and you look up videos and you're like, hey, what's quantum? What's QED? What is it? Every video starts with the same premise. Oh, it's super weird. You'll never understand it. The less you understand it, the bigger your brain is. And, the more you submit to it, blah, 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 right? All this mysticism. So we're going to get through that and see what these boys are actually talking about here. So, one second, I'll screen share here. So I'm going to start my screen share, and then there's a couple of videos that we're going to watch and skip through. And Shane's going to be presenting those because I can't present audio at the moment. So I'm going to go live here. So here's my prez. You can tune in for a second, and then we're going to switch to Shane here in a minute. All right. So Shane, the 18-minute video. One second. I got you, bro.
By 18, you mean 15?
No. Here you go, buddy. Okay. I put it in the live stream text chat 1.
Okay.
All right, cool. I had a feeling that would happen. How did I know? Psychic? Superposition? Quantum effects? Is there quantum foam? Who knows? Okay, so here we go, lads. All right, so coincidentally, the next slide is Shane, you're up.
This is still a 15-minute video. Is this the one you want?
Yeah. Right, I'm sorry, 15. Sorry, I thought it was 18. My bad.
So it's this one.
Yep. So we're going to play out. So put it at 15, let it play out for about 2 minutes, and then you could put it at one. Yeah, and then skip to 8, and then let it play for 2 more minutes, and then 14 for 1 minute.
Gotcha.
And then I'll go ahead and join your stream as well.
15 to 2. Okay.
Stream inside of a stream. Okay. No, that's not it, sir.
No?
No. I just linked you a new one in Earth Awakening's live stream text chat. That's the one. It's from Science Click English.
Another 15 minutes.
Yeah, but save this one. We're definitely going to circle back to your girl.
Tuesday. New video.
Nice.
Electrons are not free to electron activity at this on an object force. When two electrons get close, they repel each other. This explains why we don't fall through a chair when we sit down, why we can exert a force on an object, and why the air exerts friction on a feather. Apart from gravity and radioactivity at the nuclear scale, almost all phenomena in the universe can be explained by how electrons behave. At first, one would be tempted to describe this repulsion by a force, the electromagnetic force. Electrons are not small marbles that would obey classical mechanics. They are quantum objects, particles, and to describe their interactions is necessary to reconcile electromagnetism with quantum physics.
Pause it.
To this end, in the middle of the 20th century, interactions, it is necessary to reconcile electromagnetism with quantum physics. To this end, in the middle of the 20th century, the most precise model ever created in the history of physics was developed. An elegant model which allows the use of simple diagrams to calculate with astounding precision the most fundamental phenomena of physics: quantum electrodynamics. Quantum electrodynamics is an example of a quantum field theory.
All right. Yeah, that should
We
be
consider
enough,
our
Shane.
universe as a sort of box.
Let's skip ahead to the next section.
Yeah. Is that at 2 minutes? Are we at 2 minutes yet? Or?
No, you got like
Um,
30 seconds.
Oh, my bad. Sorry. Let it continue. Right when it was about to get to the good part.
Within these fields move about small packets of energy that can appear or disappear, called particles.
There you go.
Electrons fields move about.
Perfect. Okay, so quick recap. What we're dealing with here is quantum field theory. So they have a theory that there's an electric field, and in their conceptualization of how a field works, instead of being continuous lines of force, it's actually discrete, disconnected, discontinued packets of information, and that's how it works. So when there's an uncharged particle and it comes into existence, it interacts with this field, and obviously there is a field, but it's the interpretation of it and everything else we're going to get into. But anyway, when it interacts with the field, you can measure the magnetic properties of that. They call it the magnetic moment. So that interaction, and they base everything off of the strength of that magnetic field. They reverse engineer, like, okay, so if it's a particle, it would have this much mass. It would be orbiting this fast and spinning this fast to generate blah blah blah, right? So that's kind of how it all breaks down. And then we're going to go over this is now where he starts to talk about the Feynman diagrams, and we'll get to the history of all that. But this is basically, there's a series of diagrams that you can solve to make predictions on what the strength and what the measurements are that you're going to be measuring for the magnetic moment for an electron per se, or a muon or what have you, right? So this is where they're getting all this, and then the outcome of these diagrams, right? So like, actually it's the story about the diagrams, right, that he gets into, where it's like you'll get these interactions where it's like, okay, we have an electron, and then it'll split and become a positron, and then that emits a photon that gets reabsorbed, and then the positron goes backwards in time, and then the electron comes out, and then that'll give you this much energy, right? And then they have an infinite amount of possibilities of what could happen, and they summarize it by whatever this measurement would be, and then they do their experiment, and then it matches, and they're like, okay, so this must mean that what would have happened is this diagram would have been correct, right? So they're like, okay, that's kind of how it all breaks down. So anyway, go ahead and play that out for, I think it's
To look at the outcome of each
2
scenario,
minutes.
we sometimes find our two electrons, and sometimes more particles, with some having appeared between the initial and final instance. Each of these scenarios, which start from an initial situation and reach a final situation, is called a Feynman diagram. Feynman diagrams transcribe the different possible evolutions of our quantum fields from a given initial situation. Apart from the initial and final particles, which are real particles that can be detected, the particles that act as messengers within these diagrams are said to be virtual. These are particles that cannot be detected, and they can exhibit some rather strange properties. They only serve as intermediaries to describe how our two electrons interact at a distance. Mathematically, each scenario, each Feynman diagram, corresponds to a very rigorous equation. And virtual particles are only a way of interpreting intuitively certain parts of the equations. That said, although they are only intermediaries resulting from our mathematical model, it is essential to consider these virtual particles, because they account for the interactions of the fields, and therefore how electrons behave.
Okay, so pause for a second. Okay, so what we're going over here is the is the electrodynamics, right? The mechanics of the explanation of why they're getting the readings that they're getting, right? So this is all about backwards attributing it to the atomic model, right? To get that baby atom that has a nucleus that's being orbited by an electron and a positron and all that, right? This is all to get back to that. And then we have these measurements that as we're going to learn about here moving forward, is that there were predictions and measurements that were made that were outside of the theoretical predictions. And this is the explanation that they put forward to explain why experiment didn't match theoretical prediction. So when they're talking about electrodynamics, right, they're saying that this is like the actual physical interpretation of what's happening. Like these abstract mathematical mechanics that we can't measure, the antipositrons, negative electrons, all that stuff. That's that comes out of the math, and it's represented in these diagrams. So when they use these diagrams to match their measurement, they're like, oh, that must mean our physical interpretation is correct. That must mean that there's an anti-positron pair collision, annihilation, etc. Right? Because we got this energy reading, and without being able to explain that why this energy reading, didn't match the prediction or whatever, the whole thing would fall apart. So just kind of keep that in mind about, what this actually is, like what they're actually saying, what's being put forward as the physical interpretation of reality. And that's going to be super important moving forward, because some people will say, oh, this isn't, my interpretation, or this is just a tool, blah, blah, blah. Well, it's actually the backbone of the belief system of all of this, and wave particle duality, et cetera, et cetera. So it's more than just a tool. It's the backbone of the belief system, if you will. So anyway, I think are we almost at two minutes on that? How much time we got?
20 seconds and then another minute at the end.
Perfect.
Summarize what we have so far. We describe a space-time which contains two fields, that of electrons and that of photons. From an initial situation with two electrons, we are interested in all possible evolutions, allowing interactions that link a photon to two particles of the electron type.
Sorry.
Yeah. So anyway, this is a great video, though. Highly recommend it. It's like 15 minutes long. It's a little lengthy to put into the whole pres, but if you want to get some more in depth on the interactions and all that and have it explained, highly recommend. I linked it earlier in the chat. So go ahead and play that last part, and then we're out of here.
When it interacts with a material, Maxwell's equations, which govern electric and magnetic fields, and interactions between electrons, from which at our scale almost all forces arise. Historically, this model was the first great success of quantum field theory. By describing matter as quantum fields, interactions as virtual particles, and proposing a very elegant calculation method based on diagrams and amplitudes, quantum electrodynamics has in particular allowed scientists to predict with an unprecedented precision the way in which an electron reacts to a magnetic field. Through virtual photons, the magnetic field causes the spin of the electron to precess, and this precession motion is perfectly predicted by quantum electrodynamics to almost 10 significant figures. To this day, all theories considered, this is the best verified experimental prediction in the history of physics.
Well, case closed, right, boys? That's a wrap. It's a wrap. Okay, cool. So now we're gonna look under the hood and see what's up with that. So now, if you'll turn your attention back to my stream. sorry about the back and forth, but it'll be worth it, I promise. Or if it's not, you can leave a complaint, and that'll get figured out. Thank you. Okay, I'll give a minute, or I'll give a couple more seconds for the boys to file in. I'm gonna hit this water real quick.
I think you can file it to Stone in the QC department. He'll personally take all complaints. I hope he's not here to hear that. Oh, he's here. Damn it. Sorry.
Awesome. Shout out to my boy Stone. All right, head of QA. Yeah, he will see to the complaints. Okay, so here we are. So we finished up the video. So here we're going to look at, okay, so wouldn't there be a competing theory? Wouldn't they all be in on it? Well, if a bunch of guys got together annually to meet up and do, and to converse about what they're going to put forward as the physical interpretation of reality, well, that's what we have here. So this is going back to the Solvay conferences, and then the more modern ones, of course. Yeah. So we have the cast and crew here. So we have all the boys. We got your boy Schrodinger. Shout out to him. Actually, never mind. He turned out to be a bad man. We got Wolfgang over here, Heisenberg, Professor Fowler, lots of boys. Dirac, little math wizard. Arthur Compton, known for Compton scattering. Very cool experiment. Get your boy D. Broglie, right? Max Born, who introduced the idea that if you actually square the solution to Schrodinger's wave equations, the probability that you will find the electron will be in there. So when you hear about the cloud of electrons and where's the electron, we can't find it. Well, proposed by Max Born in 1926, that's where that came from. So the Copenhagen interpretation of QED, that's where all that comes from. So here we have Niels Bohr. He's also involved there with the old atomic model. Max Planck, Lorentz, of course, Einstein. We got your boy Paul. Oh, dude, I can't do it, but a stone, if you're able to shout it out. Paul.
Stress falling into stone.
Dude, I'm doing it, bro. I'm doing it. I'm in. Nothing? Okay, cool. No worries. I got you, bro. Okay, so Paul. And then anyway, this guy actually proposed the solution for the Sagnac effect for your boy Einstein, helped him out a great deal. And then they ended up not going with it anyway because it just confused the hell out of everyone. So after that, I think that's it. So anyway, these boys all got together annually, met, and it continues on to this day. Very cool. Now, the other part of the cast and crew is going to be the electron, right? So this is the basic for subatomic particle interaction. 1 second, I got some DMs here. What did Schrodinger do to become a bad lad? Apparently, he was a vicious pedophile.
Checks the box for me.
Yes. Yeah. So that's not good. Yeah, I totally forgot about that. I just learned about that recently. So anyway, we have the subatomic particles. Anyway, this is the baseline for how they started the reifying the atomic model, right? Because before this, your boy J.J. Thomson was working on a very nice and clean vortex theory based off of a fluid medium to explain the molecular structure of everything. And then he did this experiment here, and then this kind of was put forward because it was much easier to explain, and at the time, the mathematics to explain fluid dynamics sufficiently did not yet exist, and this experiment really put things forward. So we're going to go over how they came to, how they get the stats for this electron, how they figure out its weight, how's everything made up of electrons, how do they know this? Well, J.J. Thomson took this vacuum tube and I have the year in the notes here, in 1897 here, and when you hook up power to this anode and cathode here, it's going to shoot out electricity, and they have the ground here has a little slit in it, so it's going to facilitate like a coherent beam, coming out of that. There's going to be, a coherent beam of electricity coming out of there, and then they have a magnetic and electric field at the middle part of the tube here that they can introduce, electricity and a magnetic field, north and south, and they can measure the deviation from the center on the other side of the tube, right? So when there's no field here, it hits perfect center. And then when they introduce a magnetic and electric field, they realize that, what they're dealing with moves towards the positive charge. So they're like, okay, this is quote unquote negative charge, right? This is where like all this comes from, even though there's no actual negative charge, like it's not carrying an absence of charge, right? That's not a real thing. It's just a way to describe high to low pressure mediation. And what this is in this system, when they were doing this experiment at the time, this is the lowest amount of energy that they could introduce into a system, and then get, and then get deviations with the magnetic field and electric field, and make actual measurements where they can go, okay, it deviated by this much, right? So with that, that's where they actually, there's a little more to it, but what they did with that information, right? When you know how much energy you're putting into the system and you know how much it's deviating based off of the strength of the other things, you can reverse engineer the quantization of what the particle would be algebraically. And then once you have that, you can you distribute that energy over the radius of a sphere. So you just come up with a coefficient for that. So J.J. Thomson had a coefficient for that, and it was 1/5 times E squared over mu times A, and mu and A were the, the strength of the electric field and the amount of charge that you're putting into it. So L, yeah, and then the A would be the radius, right? So when they had that, so once you have all that and you make those assumptions, you can quantize it and you can look at this like a ballistic projectile and you can go, okay, we're shooting little baby beams and, when they're interacting with this field, blah, 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 right? So that was a much easier way to interpret it. And with that, everything really popped off. So when they talk about electrons and all that, this is the lowest energy state that they could measure at the time. And this is the baseline for everything upon which all else is based on. So then we got the muon, very similar to the electron. It just has if I remember correctly, it has a different magnetic moment. So the magnetic field strength that it generates is slightly stronger. So they say it's heavier than the electron or whatever, right? Because this is what all these relationships are based off of to reify them as quantized physical particles that are interacting with a discontinued discrete packet energy field that's definitely not connected and definitely not a fluid medium. All right, it's just abstract math, boys. Don't conceptualize it as connected, right? So we got the muon G-2, right? They call it, and be very specific here. It's very important. Pronounced G-2. Don't call it the muon G2 or anything like that. They got to hit that minus sign. Very important. So here they say they measured the magnetic dipole moment of a muon to a precision of 0.14 parts per million. So what they're saying there is that they've measured that strength of that magnetic field down to 1 in 14 million, right? So that's how they base everything off of that, and that's when they talk about the accuracy of that and the predictions. This is what it all comes out of, right? So there we go. So to kick us off here, we'll go over Lamb shift. So to start us off, the backbone of quantum electrodynamics started from quantum field theory, which was started by Paul Dirac, and there was predictions made with how the atomic structure would interact with with what makes up the subatomic structure of things like electrons, right? And how that would interact with this quantized, discontinued, discrete energy packet field that they call the magnetic field, right? So there was a predicted amount of energy for hydrogen, right? So they said that in their model, they have hydrogen being orbited by 2 electrons. So that should produce a specific amount of energy. And when they took, spectroscopic readings on hydrogen, they found that the energy emissions were slightly higher than what was predicted, and they didn't know how to explain that. Now, normally that would be a falsification of the model, right? But with a little mathematical dabble-de-do, the boys came in and explained it through quantum electrodynamics, and we're gonna now get into that. So there was an experiment. This is the Lamb shift that was done by your boy Willis Lamb, and that was where they were measuring the electrons in hydrogen, right? And it was outside of the parameters of quantum field theory. So we'll get into what all that means as we go over the history of the equations and what was put forward as the physical interpretation. So how did we get to experimental measurement not matching prediction being proof of the model? How did we get there? Well, it's a nice journey. Luckily, our boy Oliver Kanza takes us through it here. So this is titled "Something is Wrong with QED." So I'll read a little bit here from it. So it says, however, the precision is based on a single experimental value, the anomalous magnetic moment of the electron, the G factor. So that magnetic field we were talking about earlier and the strength of that they use to quantify everything as a particle. So the value obtained here, it was in a very suspicious way. Oh, no way. So as they move forward in time, their mathematics are going to start matching the experimental prediction. And then in some cases, it's going to be the dudes that make the prediction are the same dudes that did the experiment. And what do you know, boys? It matched. It just happened to match. So a lot of this is going to hinge on the boys Carr, Plus, and Kroll. So we'll get to know them. And they did a little presentation of their mathematics where they claim to, derive solutions to Feynman diagrams that are physically meaningful, but we're going to learn that they're not. And then we're going to learn about the mathematics behind QED. Like what's the fuel that drives the engine, right? Well, the fuel that drives the mathematic engine of QED is called renormalization, right? Because all these equations, right? That Feynman diagram, that nice eloquent diagram and equation that we just looked at earlier in the video, right? All of those solutions diverge to infinity, and that what that means is that they're physically meaningless interpretations of reality in terms of like the story of, oh, there's a virtual particle and all this stuff, right? Because what they have to do is they have to do various mathematic techniques to what they call renormalize them, right? So they're reining them in to make them converge instead of diverge, right? So they're trying to extrapolate they're forcing their physically meaningful calculation out of it instead of it being a consequence of the theory naturally, and, supporting it mathematically in a coherent way that makes sense. And this is a heavy burden that weighed on the godfathers of QED, and we're gonna learn all about that. So this is from Paul Dirac here. He said, "Oh, are there any questions so far? I've kind of went over a lot. Has anyone got any questions?"
Yo, this guy Flat Monkey's trying to ask you a question. Can you hear him?
Now, what's up? Zach. What's up?
I was just gonna ask. Already got an answer from Shane. I've been trying to ask for a while when your presentation was going to be done, so I can come back when it's over.
Oh, yeah. So we got. You're free to leave whenever, buddy. So anyway, the renormalization here.
Hang on, before you go, I just wanted to say something. It's in CBR1 here. Can you hear me? Sorry to cut in just as you're about to begin. I think it'd be good if you keep reminding people as you're speaking that they are not giving us reality. They are bending reality with their model. Okay, because you said the reality is they're lying about reality. Can you please make that clear? Thank you.
Yeah.
Support quantum dynamic theory as the best theory that ever predicted anything ever. Jen, are you sure?
Yeah. Cool.
They're bending reality. They're not telling the truth, are they?
One sec. Oh, is that? It's your boy. What up, Jen? 1 second. Okay. Here we go. So let's see. Where were we at? Okay. Yeah. So let's see what the godfather of quantum field theory has to say. The renormalizations we have in our present quantum electrodynamics comes from starting off with what people call a bare electron without an electron without any charge. At a certain stage, one brings charge to the theory, and that makes the electron what it is, and thereby that interaction is what causes the problem. Because once you do that, you introduce perturbation theory into the equation, and that's what causes the divergences to infinity for them and makes them unsolvable and physically meaningless. So these bring perturbations into the equations and causes changes of the mass of the electron by delta M, which has to be added to the previous mass of the electron. This procedure is a rather roundabout because it starts off with the unphysical concept of a bare electron. Probably an improved physical picture of QED, we will not have a bare electron in existence in the theory, right? So this all starts off too, like it hinges off of the principle that there's this uncharged nothing, there's this uncharged thing, right? And then it comes into existence, and then it interacts with the magnetic field, and that's what's generating what they're measuring. And then to describe that interaction, because it has to be discontinued packets of energy representing the field, and when that causes, or when they have that interaction, that's what's ruining everything, right? So to So to rein it in, they have to renormalize everything, and we're going to see, we're going to just keep learning about that. So there are two classes of difficulties. So he goes over the first one, and this is the second class that he's talking about, and this is the renormalization. They arise primarily from the fact that when we apply our theory to quantum fields, we have to make it agree with the theory of special relativity, interpreting it in terms of three-dimension sections. I have mentioned we have equations that look all right at a glance, but when one tries to solve them, we find that we don't have any solutions. And that's not good, right? So, and then he goes on to say that they found some, ingenious ways to do some roundabout gobbledygook. And then one gets integrals that diverge instead of converging into something definite. And physicists have come up with ways of handling these. And this method is known as the renormalization method. The renormalization theory has removed some of the class 2 difficulties if one can accept the illogical character of disregarding infinities, but it does not remove them all. Yeah, it does not remove them all, and that will be a huge problem that we'll learn about at the end here, or later towards the end. And then he also goes on to say that he wants to reintroduce a picture of an ether, right? And he goes on to make it clear. He says, I do not mean to introduce the old idea of the ether, that you suppose that it's a fluid medium that fills up the whole of space, that anything in that space would have a definite velocity relative to it, right? So that was what the whole Michelson-Morley debacle was over. So this is why they had to come up with a discontinued discrete packet field and describe everything in this absurd way, because they had to remove the ether because of the implications of the Michelson-Morley experiment. If you don't remove the ether and you accept the measurements as they are, the implication is that the Earth is stationary. So to get away from that, they were like, oh, there's no ether. The measurements were actually a null. Don't look here, no ether. But in reality, right, they're still doing experiments. They've got these measurements. Everything is still, there's still an ether, right? So how do they hide it, right? How do they obfuscate it to an absurdity that when people go to think about it, they're like, oh, it's just a really difficult thing that if you don't understand it, then you must be a dummy. It's like no. They went out of their way specifically to make it this way because of the implications of earlier experimentations and the mathematics, and the reason that they are like, well, this is just good enough, and they have to go with it because there is nothing else, right? This is the best they could muster. So it would however mean the departure from the notion of the vacuum that we have in the quantum theory, that we start off with the vacuum of having the symmetry required by relativity. So relativity says vacuum is empty. Quantum field theory says vacuum has vacuum energy, vacuum perturbations. There's polarized vacuum fields. There's some sort of field in this vacuum. So if you ever looked at Maxwell's equations and you see the mu and epsilon, that's the magnetic permeability and magnetic permeativity. So that is the lowest amount of impedance that's in a vacuum. So that's where all this comes from. This is oscillations in a medium, and this is how many oscillations you would get in that environment, right? Very cool. All right. Oops, 1 second. That did not change properly. Okay, I think we're good now. So why is the father of QED and QF quantum field theory and QED going back on the ether and talking about continuous lines of force? Well, turns out your boy had a brain. So now it starts. I'm just kidding. That's a bit aggressive. I'm sure the quantum lads have brains too. Now, the state of affairs is just what we have with the discrete lines of force. We can picture that the lines of force as strings, and then with the electron in the picture is at the end of the string. The string itself is the Coulomb force around the electron. The bare electron means the electron without a Coulomb force attached to it. So it is inconceivable to picture this without inconceivable to think about that, the end of a piece of a string, without thinking about the string itself, right? And he says that this is the kind of thing that you should incorporate in your theories, instead of saying that that there's no string. It's just the end of the string, boys. So he goes on to give his 2 cents on the muon, because I kind of relate to this a lot, actually, and it was kind of cool to read this. So it says the muon has a surprising property of being almost identical to the electron, except in particular, namely the mass is some 200 times greater than the mass of the electron. And again, this is in relation to the strength of the magnetic field that it generates when it's interacting with the fluid medium known as the ether, and in quantum land known as the magnetic field. That's not made of continuous lines of force. Let's see. So the same spin and same magnetic moment in properties as it does for the electron. And it just it leads to the suggestion that the muon should be looked at as an excitation of the electron. But if the electron is a point, picturing how it becomes excited is quite awkward. But if the electron is in the most stable state of a finite size, the muon might be the next most stable state, which is, just undergoing a type of oscillation. So it's just oscillating faster. And then on the right here, we're looking at a diagram of continuous lines of force that diverge and converge in on themselves. And this is what he was conceptualizing, how an electron and positron would work, right? So he completely was moving away from the idea that these are little elastic spheres that are orbiting other elastic spheres that may or may not be having collisions with a discontinuous discrete energy packet field. And I'm going to keep saying it that way because it sounds ridiculous, and it should be. All right, so here we have infinities and how to deal with them. So we talked a lot about renormalizations and how that kind of puts a damper on the physical interpretation of the equations that they get, right? So the physical meaningfulness in the interpretations, really rely on the solutions of the math, right? And if the math is just gobbledygook that's being facilitated to give the outcome, then it doesn't mean anything, right? So we'll look at the techniques that they use here. So they'll do substitutions. They'll just straight up replace a divergent series with a finite series that will give them the convergent result. Let's see. Second, gotta adjust this. There we go. Then we have separations, right? So they'll break the equation up into 2 parts. So they'll separate like the UV spectrum from the lower spectrum, and by doing that, they'll go, okay, well, these ones diverge to infinity, the UV spectrum stuff, and then the other stuff doesn't. So we'll just use those. So they'll just completely ignore it. Right. So this is what Dirac was talking about when he was like, yeah, if you're cool with just, doing whatever you want, then yeah, it's all gravy, dude. And then there's cutoff points, right, where they just arbitrarily decide that, yeah, we're good here. oh, we've reached experimental value. We're set. Okay, cool. All right. So all of that mathematics, right? When people talk about wave particle duality, the uncertainty principle, the collapse of the wave function, the quantization of the electric and magnetic field as discrete packets, polarization of a vacuum energy, self-interaction, particles traveling back in time, virtual photons, electron-positron, pair creation, and annihilation. That's what they're all talking about, and it's all supported by math that has to be rounded, like just rounding off to the nearest whatever gives them the solution that they need so that they can keep the idea alive that their interpretation is the correct one. Right? So imagine you were taking a test. Remember back in math class when you were learning about rounding and stuff? And like, imagine you just had the freedom to just round it whatever you wanted. And the teacher was like, great job. You matched the prediction or whatever, right? And it just has no meaning, right? So that's kind of what's going on here. So back to the paper here now, we're going to go over we're going to get more in depth now on the history of these equations, because it turns out to do this whole renormalization process, they've had to adjust coefficients, multiple times over the course of 60 years. They had to, their constants constantly, right? They've adjusted their constants for new experimental values, and then suddenly their math just happens to fit it. Like all this rigmarole keeps happening under very suspicious circumstances, as my boy Oliver over here says. So here we'll learn a little bit about how they put this forward and like why they had so much credence and whatnot. So this is these meetings and stuff that we were looking at earlier where the lads were getting together and bringing all this forward. So all these people, a lot of them participated in the Manhattan Project. So they had a lot of background, or they had a lot of prestige from, you know, the success of the atomic bomb, right? And, you know, we're all familiar with the atomic bomb, so I'm not going to get too in depth on that, but they were, you know, riding the success of that. So they had a lot of lead in terms of universities and what they could do with research and what they could put forward, you know, just based off of their ideas in math, and nobody could question them. Right. So I think that pretty much rounds it off on that. So yeah, and then like, and those people like all went on to become like the heads of the universities, the heads of the research people, and then like you would get, you know, grants from the government if you agreed with what they were putting forward, right? So there was no chance that someone was gonna, oh, by the way, hey guys, continuous lines of force. Like nobody, that's not, or you know, nobody was gonna come forward and do that, right? Because you were gonna get ostracized and rejected, right? You know, you weren't smart enough to understand the quantum lads. So here we're going to read from Dirac's biography here. So it says, he strongly felt that quantum electrodynamics in its 1936 version and its 1950 version was intolerable because it was complicated and ugly. And he's, of course, referring to the mathematic techniques used to solve the equations because they never actually were able to solve these problems in a way that would be physically meaningful and consistent with the mathematics that they were using to, you know, explain it as a physical theory. So it was just not sensible mathematics. Sensible mathematics involving neglecting quantities, which is small, is fine, but neglecting quantities just because it's infinity and you don't want to deal with it is, you know, it's not cool, man. It's not cool, bro, as the kids say. And Dirac says that, you know, he admits that from an intermentalist point of view, renormalization is an undeniable success, right? If you're looking at it from a pure standpoint of you don't care, you just want the answer, dude, QED is your boy. But at the price one must pay for this success is to abandon logical deduction and replace it by working rules, you know, by basically, you know, play a mathematical symphony that you have to play to solve the equations, to, you know, to extrapolate your coveted physical meaning. And this is a very heavy price that no physicist should be content to pay, right? So this is the father of QED, right? So when people were like, oh, it's complicated, you don't understand, this guy understood it. I'm pretty sure he got it. Pretty sure if you gave him a QED test right now, he'd pass the crap out of it. All right, so he goes on to say here, so this is from an interview from, what's the year on that? Well, it's not 2013, but that's when it was published. So we have an interview here from David Pete and Paul Dirac. He says, would you comment on the divergences and infinities which occur in quantum field theory? Many think that they can be removed by renormalization. Is that your feeling? He says, it's a stopgap procedure. There must be some fundamental change in our ideas, probably the change just as fundamental as the passage from Bohr's orbit theory to quantum mechanics. When you get a great number turning out to be infinite, which ought to be finite, you should admit that there is something wrong with your equations and not hope that you can get a good theory just by doctoring up that number. And the guy says, oh, snap, that's crazy. Well, let me ask you this then. Some people have suggested that introducing curved space-time will get rid of these infinities. Your boy Abdus Salam is working on that, for example. And Dirac goes, yeah, I don't care. That's still R-worded. So that's, you know, doesn't mean anything. All right. So, and here we have Feynman's thoughts on it, right? So this is the Feynman diagram, lad, right? So this is another QED father. And we're going to hear his thoughts on the renormalization. So he says that they use some theoretical numbers that are not directly observed in any way, but they get the equation, or the, you know, it gets them it puts gas in the tank and gets them where they're going. And he says the shell game that we play is to find these imaginary numbers, and this is technically called renormalization. But no matter how clever a word, what it is I would call it a dippy process. Having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent, right? So this big burden, the big burden of proof, right? The big physical meaningless of the solution of these equations right? It's the most accurate predicted value in measurement. Well, it all comes from this, and you know, we're looking at how you solve it, how you put the pieces together. I suspect that renormalization is not mathematically legitimate. All right, so that's Feynman's thoughts on it. He's not too fond of it, but he's always down to play, you know, and that's kind of what I respect about Feynman. He doesn't care. He'll literally tell you, shut up and calculate. He told a group of grown men that, and that's like the famous quote that everyone's touted as like a good like as if he put forward a good argument, because we're going to get to the context of shut up and calculate here in a minute. Oh shoot, big math screen. What do we got here? Okay, so earlier when we were talking about the Lamb shift, right? And this is the backbone of QED. This comes from an experiment where the guy Willis Lamb was measuring the the electrons in hydrogen to see if they matched the amount of energy that they expected if everything was interacting with their version of the quantization of, if everything was interacting with the quantized field as predicted by Dirac's equations for quantum field theory. And they didn't get the, you know, obviously they got the value that was higher than the predicted amount. So your boy Beta comes in and he's like, hey, using this equation that I just wrote off the top of the dome ski, we can solve this. It's no big deal, boys. And this K value here that he has in the equation is the issue. This is a series that diverges to infinity. And later he would go on to correct this, right? So like, this is one of these, this paper is really cool because it's not like, he doesn't have to go through a bunch of math that no one's ever going to understand. He's just, because this is already like corrected history, already been rectified. So he's just going over the history of it, right? So we don't, you know, you don't have to get too carried away with it. You just kind of take it for what it is. So anyway, he made a mathematical faux pas here to bring the theory back in alignment with the measured values. Because he was like, oh, you know what? Actually, if we apply this value to Dirac's equations, right, we're actually good, dog. And we predict the Lamb shift value of this. And everyone was like, oh, sweet, right? And then he had to, well, we'll get into that later. Well, I think that's it. Okay, cool. So next we have, so anyway, his thing diverged to infinity. It was full DS, and then he kind of drops off. And then our boy Schwinger comes in with his own solution, and he uses the very elegant, because this is crazy looking, right? What is this? This looks like, this is disgusting. Your boy Schwinger comes in with G equals 1 plus alpha over 2 pi, right? And that gave the predicted value for Lamb shift. So he's like, dude, if we apply that, we're good. Now he couldn't. Now the issue with that is, what made you divide it by 2 pi? What made you do that, bro? So this is one of those things in the math where they're like, well, you can't just, like, it's cool, you can do that for sure, but why'd you do it, right? How'd you derive it? As a consequence of what, right? Where in Dirac's equations did you pull out 2, like, you know what I'm saying, right? So this gets into like showing your work kind of thing, right? Remember when we all had proficiency tests in 5th grade, and there was the 2 questions that were on the math section. Everything else is multiple choice, but there was 2 questions. We had to show our work that we could do long division, right? And do multiplication, right? We had to write it out or whatever. So this is heavily on showing the work, right? Because this is what is this is what's keeping the story alive about the particles and the little elastic spheres and rotate, you know, and all this stuff, right? So, excuse me. So there's a conference put together in 1948 called the Peccano Conference. And this was put together by, I believe, Oppenheimer. And him and Feynman were, I'm kind of skipping ahead here, but him and Feynman were supposed to present how they derived the Feynman diagrams and how they derived dividing by 2 pi. Let's see. So, oh yeah, real quick here. So you can do, so in the math and in physics and all that, what you can do is you can interject like a fudge factor. And like what he did here, the author of the paper suspects that what he did was numerology, because when you divide the answer by pi, it gives 0.1, and it's very close to the difference in the experimental measured value. So he just threw that in there for 2 pi because 2 pi is about 6. So he just divides by it's just, they call it numerology. So he just did some gobbledygook and everyone was like, cool. How'd you do the gobbledygook? Well, he did a 5-hour presentation and everyone was mad at him because he couldn't explain it. He still failed to explain it. So Feynman gives his presentation and we'll get his commentary on it here. So this is Feynman trying to explain how he came up with his eloquent equation and diagrams. So, but the meeting was very exciting. Schwinger and I would talk to each other, but we would compare notes and our respective results, where when he would tell me where his terms came from, and I would tell him where my results came from for the same. And we did not know how each other of us had done it, but we did agree on the answer. And he's like, well, nobody, we would talk about our physical ideas and see that the result would be the respective calculation, or would be a result of the respective calculation. They would talk back and forth about going into the details, but nobody understood either of them. And then he goes on to say, for this purpose, Feynman was not only on the path forward in this time, but so this is where Feynman's proposing, like, electrons and positrons and stuff going back in time. So for this purpose, Feynman was not only the path in which is forward in time, but also the path which goes backwards in time, in accordance with the idea which he had learned from John Wheeler as a graduate student in Princeton in 1940. Which I think there was some controversy where I think it was Feynman who used a student to like solve a bunch of stuff for him or something, that they were talking about a little bit in there too. But anyway, so now we're introducing like something going backwards in time, right? And people are like, what are you talking about, bro? Like, this is physically repulsive. It's disgusting, right? They were all upset. And, but basically they didn't really have any other way, to keep the theory alive, right? To keep it consistent with the experimentally measured values, unless they went with this craziness here, right? So we'll read a little bit more here. So this is from Feynman. So he says, this is Feynman addressing the crowd, right? This is my mathematical formula, and I'll show you that it produces the results for all results for quantum electrodynamics. And then he was immediately asked, where does the formula come from? It doesn't matter where it comes from. It's the right formula. Dude, what? That's crazy, right? So how do you know it's the right formula, people ask? Because it gives the right result. How do you know it's the right answer? And then it just goes back and forth, right? And it became evident because people wanted to know, how is this a consequence of Dirac's quantum field theory equations, right? How did you get here, bro? This isn't, I don't know. It should be very straightforward, right? Like, this is dubious. So anyway, how do you know he gives the right answer? And he just goes back and forth. What made you think the formula was right in the first place? I tried to get into the deeper physical ideas, right? So he starts talking about going backwards in time, and then everyone was like, yeah, this is full DS. I'm out of here. Right. So after that, yeah, people were just dissatisfied with his solutions, right? But there's one more issue here, and we have to roll in general relativity here. I'm sorry, not general relativity. We have to roll in relativity theory here. So your boy Tamanaga has to bring in his version too, because what they're going to do is they're going to merge all three of these, all of these mathematically inconsistent theories. They're going to merge them all together and then use them as the backbone for, justifying quantum electrodynamics as being, which should have been the falsification of quantum field theory. They're going to use it. This is how it becomes proof of the theory, right? So shout out to your boy Tamanaga. So he says here in this article, he has pointed out that the existing formalism of quantum field theory is not yet perfectly relativistic. And he goes on to say that in equation 1, that the how they're using time, it's distinctly different from the other parts of the coordinate system. So it's like, it's not what's the word I'm looking for? It's not just another thing like it should be if it was an XYZ. So he's saying it's like significant. And then they're also in relation to instances where they're like talking about quantum entanglement and stuff like that, where they have the same timeline. He's saying that's not symmetrical with Lorentz symmetry, because there has to be proper time and then the deviation from proper time. So there has to be some rest frame somewhere, and then it has to be relative, like the motion or the deviation in time has to be relative to that rest frame. And he's like, that's not addressed in the equations currently, where we have superposition, right? Because they share the same timeline. So this guy, he's like, hey, I got you on the equations, boys. No worries. I'll hit you up. But my solution has the same problems as everyone else's, and it diverges to infinity. So you guys are going to inherit the same problems as mine. But I got you on the math. Should you need it in the future? Should a hero come along and save us mathematically? We're all packed up and ready to go. Okay, so what we're going to get into next is our boy Dyson. So Freeman Dyson comes in with his Dyson series to solve these equations, right? To merge all these together and give a way to solve them. What he does is he uses a Heisenberg S matrix series, and then he just keeps adding on to that. So as you see, the first series is nothing, and then it goes to 2, 3, 4, etc., right? So he keeps doing these, and then that gives them the ability to bring them from divergence into what gives the appearance of convergence. So there's actually a video. Oh, this was a great. There's actually a video here to play, but we're not going to skip for this because it's only a minute long. I'm just going to reiterate, and I'll do my best British accent. No disrespect to you, your boy Dyson here, but this is my best British accent. I know Shane's about to take his headset off right now. Hello, lads. I'm from jolly old England. I'm Freeman Dyson. They asked me. Oh, it's into an Australian accent. Okay, sorry, I can't do it. Okay, so anyway, he says here that they asked him to, figure this out, to all three of those equations, all three of those guys' theories, right? How do we put them into a cohesive way to explain everything mathematically? He goes, okay, we can hit up this Heisenberg S matrix series and and just do that, and they call it the Dyson series now. And then he goes on to say, but then I actually came across an argument in the summer of '52 that I found to be irrefutable, and the argument's quite simple, and it removed the physical meaningfulness of the solutions that we were giving, because the equations diverge to infinity anyway, regardless of using the Dyson series, which is, he's the Dyson lad that uses his series to bring them into convergence. So we'll get into what that argument is here in a few slides. But this is the other father of QED, right? So after he realized that argument, he packed up and left QED a couple years later and went into other fields of physics. I think he went into astronomy, actually, or something like that. But he completely dipped out on that and was like, yeah, almost wasted a whole bunch of time on that. Because anyway, he was super pumped to to get this job to fix this mathematical construct, and then when he fixed it, he realized that he didn't, and it was all a ruse. So that sucks. So let's see, we already touched on Dirac's or what Dirac said about it earlier, but this is just kind of reiterating the problems here. So they have some stipulations here for quantum field theory. They got to make, or QED, they got to make it work with relativity theory, and they have the diverging to infinity problem, which has no actual solution. And then now we enter the Pope of Physics, right? Otherwise known as your boy Enrico Fermi. So this is a meeting between Dyson and Fermi. So when Dyson met him in 1953, Fermi welcomed him politely, but he quickly put aside the graphs that he was being shown, indicating agreement between theory and experiment. His verdict, as Dyson remembered, was, as there are two ways of doing calculations in theoretical physics. One way, and this is the way that I prefer, is to have a clear physical picture of the process you are calculating, and the other is to have a precise and self-consistent mathematical formalism. You have neither. A stunned Dyson tried...
Real quick.
What's up?
Is this Dyson of the Dyson sphere and Fermi of Fermi's paradox?
I don't think it's Dyson of Dyson sphere, but maybe, and it could be Fermi paradox guy.
Also, who was the guy? Bro, I got like 37 questions.
What's up? What's
Are you
up?
taking questions at any point, or
Yeah,
want to
let-
mess your whole thing up?
Yeah, let me read the rest of this slide and we'll hit a couple.
All right.
All right, so a stunned Dyson countered by emphasizing that the agreement with experiment and the calculations. Fermi asked him how many free parameters he had to obtain the fit. And smiling after being told 4 by Dyson, Fermi remarked, "Oh, well, I had a friend. I remember an old friend, Johnny von Neumann, who used to say, with 4 free parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk." There was there was little to add. In retrospect, Dyson was grateful for Fermi's rather burlesque judgment, saying that he saved me and my students from getting stuck in a blind alley. So yeah, after this, like, he pieced out, because we'll get to his argument too that he, came up with himself to end it. But we'll take a couple questions here. What's up?
The guy that was doing the formula with 2 pi, he just pulled it out of nowhere. He was like, "Let me just try 2 pi."
Yes. Yep. Yeah, I got some.
And that was Schwinger or direct?
That was Schwinger.
And then what? Feynman tried to fix it and couldn't?
So Feynman had his own interpretation of how to get the answer, and that was through his diagrams and the equation that he had. And then when people were asking how he derived his equation, he said that's where he got shut up and calculate. Right? He just socially shamed him.
Feynman said that?
Yeah.
Like,
Yeah.
sit down, boy. You don't
Yeah, because
challenge.
he got fed up with trying to explain it. Like that meeting at Ponchico or whatever it's called. Yeah, Ponchico was a complete disaster because it hinged on because that guy, right, Schwinger, was like, "Yo, boys, solved it. We're good." And everyone was like, "Oh, bet. How'd you do it though?" And he was like, "Ooh, let me hit you on the back burner in a couple months, and I'll do a little presentation for the boys, right?" And then so that's where all this came from. And then Feynman did the same with his thing, and Oppenheimer was like, "Oh, hey, why don't you guys present at my thing, and we could build off of this and explain it or whatever," right? So the boys showed up to explain how they derived QED, and then let's see. So the boys showed up to explain that, and then they couldn't, right? Because there was no actual reason for how he derived 2 pi to give the solution, right? It just gave it. So then he was like, "This is."
What was this the solution for?
To explain the energy discrepancy between how much the predicted value was from Dirac's quantum field theory and how much they experimentally measured for the Lamb shift, and that was where they were.
Question,
Go ahead.
real quick. When you say like diverge to infinity or whatever, converging, I guess it doesn't matter, to infinity, you mean like in other words, there's like always a remainder, so they're never getting a predicted solution. Is that what that means?
I suppose you could look at it like that. Yeah.
Okay.
Yep.
It
And
should never go to
then
infinity. It should always be a equal. In other words, it's not the equation ain't solved if it goes to infinity. Is the way I was taking it. That's why.
that's correct, right? So that's where they get to interject different terms, and that's why your boy Fermi is saying, "Wait a minute, how many free parameters did you have to do this?" And he's like, 4. I was like, "I don't give a sh-" He's like, "I don't care that it matches experimental value. You can literally do anything with this."
You can
Right?
make any model, right?
Right. Yeah, because that's so yeah. When they get into the math, they have coefficients, right, which are constants. You have constants, and you have free parameters, which you can use to adjust constants in the equation, right? So if you can make adjustments to all of that, then it doesn't matter if your mathematical prediction meets experiment, right? Because you can make it do whatever.
Right, and then
You saying a free parameter?
Later,
Yep.
yeah, and trying to explain later. You use this free parameter, and then maybe possibly come up with an explanation for it, or maybe not.
Exactly,
Right.
dude. Exactly, bro. And then that's where you get into quantum chromodynamics, right? Where because this is all about pressure mediation, right? So like, oh, how do we explain pressure mediation as discontinued packets of lines of force? Like, okay, so we have these other things called gluons that exchange information that live inside of the center of the electron. And that is like, dude, what is happening right now? And this is all to explain everything in a way that keeps it coherent without ripping itself apart, right? Because you get the strong force and the strong nuclear force and the weak force and all that. How do these things not rip each other apart and collapse? It's like, well, that's where they introduce quantum chromodynamics, which is just another imaginary thing to explain pressure mediation at this microscopic scale between these little elastic spheres that they've modeled out. And it's like, how do they exchange information and not do that? It's like, well, this gluon is in, it's talking to it. It's like, it's like, okay, cool, dude. So now we're 8 layers deep in a mathematical abstraction to keep the car going, right? Because nobody wants to get out. Nobody wants to admit that the ride's over. So was there any other questions?
Yeah. A free parameter is a thing you can use to change a constant. That's what it does.
You can just interject it into the equation to like round off whatever you need to do. And then it's like, well, why'd
It's like
you
a
do
wild
that?
card.
Exactly. And he's like, how many wild cards
Like
you
we're
put
playing
in?
poker and 2s are wild, and you got a couple 2s.
Right.
You
He's
got
like,
4
we-
2s.
right. But then you can't explain how you got the 2s. It's like, did the dealer give him to you? It's like, he hasn't dealt. It's not even, the game hasn't started yet. Where'd you get your 2s? And he's just like, well, I mean, well, if you go backwards in time, like, so that's kind of like what we're dealing with. That's a good way to think about it. Absolutely. All right, so we'll continue
I call
on.
them get out of jail free cards, man.
Yeah, they're like, and they have unlimited of them, because there's no alternative, right? They're always talking about, oh, a better theory will come and supersede it. No, not when you have the theory and prestige and mysticism surrounded with this, right? Because everyone like just believes this and wholeheartedly is like, oh yeah, it's too complicated, like, dude, nah, it's made up and it doesn't work.
Right. If they would go back to the drawing board and find the actual solution, they could start off on a better path.
Yeah,
because
because
they refuse to let go of shit, dude. Like same
Yep.
with the Helios model.
Yeah, because here's the thing, right? They're doing experiments, they're making measurements, there's applicable technology, there's ways that they're there's ways that they're manipulating these things to make the measurements consistent and repeatable, right? It's like, so what are they doing, right? Well, it's not involving electrons and interacting with the discontinued discrete energy field packet, right? Or anything like that, right? There's something else going on, because this is the battle. You can think about this like for the battle of your mind, right? You're going to conceptualize everything as a little tiny atom that's surrounded by little elastic spheres that are doing these quantum interactions to explain everything, or are you trying to hit up a different interpretation, right? Because the way that this needs to be presented is that there's no alternative, and that this is actually experimentally correct and verified, and the only way to look at reality, right? So this is like the difference between, it's not just a model, right? Like that the way that they put forward, the way that they've presented it. So there's never going to be a situation where they're like, oh, a better theory will come forward and replace it one day. No, this is all that there is. And the only thing that will replace it will be a fluid medium and continuous lines of force, right? And that comes with a stationary Earth. So that's why this is important, right? All right. So I think we'll move on now from that slide. So Feynman he writes a warning to Fermi, because there was so this gets into the experimental values changing. So what about so Feynman gives his presentation for this predicted amount and all this stuff, right? Everything's super cool. Well, it turned out that the experiment was off a little bit, and there's a different value. There's a different discrepancy for the experimentally measured value. So he writes to Fermi and he's like, yo, don't believe anything, any solution for a muon. They call it a meson sometimes. That's what they used to be called. So don't believe anything that's used that uses a Feynman diagram to calculate a muon, because it's not going to be physically meaningful, right? So they're trying to preserve continuity here, be like, don't don't present this to anyone as physically meaningful, because right now there's a problem, right? Okay, so the coupling in the Wong-Feek. Okay, so yeah, we kind of already touched on it earlier, but the Feynman diagrams are the backbone for QED, the electric weak theory, quantum chromodynamics, quantum electrodynamics, and the standard model, right? Everything is like hinges on this, right? It's all intertwined, but it all hinges on the correctness of these diagrams and the solutions to them and how they solve them, right? So I just wanted to kind of reiterate that. So now we'll get into, so beta is going to come back. So remember that guy that used the K series divergent that didn't work? So this guy comes in again and he's like, yo, boys, we can, I just forgot about it. Actually, so, and then also the experimental value had changed too. So there was that. So he comes in again and he's like, yo, boys, I actually forgot to account for some relativistic effects. One second, I'm gonna hit this water. If I account for these effects, we're golden, baby. And, we just run into the same problem where it's like, okay, dude.
That doesn't sound thing at all right there.
Yeah. So no, it ended up being the same situation, where he was, he found relativity right where he needed to renormalize the equations and give him his value for his prediction there. Then we get into, let's see, Gardner and Purcell. So these guys did an experiment and they got another new G factor. Oh no. So this guy did all that hard work and then it turned out to be another value, right? So their experimental G factor value is going to change again. So the 2 pi Schwinger solution is no longer valid. Remember Schwingy when he came through and wasted everyone's time with a 5-hour prez where he couldn't explain how he derived anything without revealing that he just made it up. So that's no longer valid. And Feynman says, no worries, boys. We can use Dyson's renormalizations to solve everything. Right. So, and by using his solutions, that's what ended up giving Feynman that's what helped get him the Nobel Prize. Feynman, Tominaga, and the other guy, I can't think of his name, but I'm sure we'll get to it here in a second. But they all gave them the Nobel Prize because when you use the Dyson series to solve the Feynman or to renormalize the Feynman diagrams, everything, they can maintain their conceptualization of everything, and that's what all this is about. Okay, so now that we got our Feynman diagrams, we're gonna we need to have some people independently corroborate them and solve them, right? So this guy, in 1950, Karplus and Kroll came forward. These are 2 lads that were supposed to be independently verifying using the Dyson series, the renormalization techniques that Dyson came up with to solve the Feynman diagrams, to give a solution to the new experimentally measured value. Right. And these guys are like, oh, boys, we did it. We're good. So we'll get into how they did it here in a second. So before we, let's see, 1 second. Before we get into that coefficient. Yeah. Okay. Okay. Yeah. So just remember, this guy was supposed to independently verify his, and this guy was supposed to independently verify his. And the fact that they both got the same solution means that Feynman's extra super correct. Okay. Okay. So the issue with Karplus and Kroll, and this is what Dyson, now these guys didn't know about this, right? Because they were all like, oh yeah, it's all good. But what Dyson, with that argument that he came up with in 1952, that was rather simple, as he said, was that at the beginning, we watched electrons repelling, right? So he says, suppose we have an inverse system where electrons attract. And if you apply the same renormalization techniques in that system that we're using for our system where they repel, then they should give physically meaningful solutions, right? They should converge instead of diverging, right? And he found that they always diverge to infinity. And when he applied them to a vacuum and vacuum polarization, that it became a complete disaster because everything would just kind of spontaneously pop into existence and on top of each other. And it just, yeah, it was not, he was like, that's what made him quit, right? He mathematically understood that that was not a physically meaningful interpretation of reality. And, that should kind of be like a meta argument for it, right? If these are physically meaningful, if you invert it, then the equations should give a convergent series. They should converge instead of diverging. And the fact that they don't means that the techniques that they're using are physically meaningless, right? They're not accurately representing reality in any way. So unfortunately, we have a new, one second. So unfortunately, for the Carr plus and Kroll guys, we have a new experimentally measured value by Franken and Lebes in 1956. So this ruins the the Schwinger value, of course, and the coefficients that were used by Carr plus and Kroll to these lads to solve the Feynman diagrams, right? So, so that's super unfortunate, right? Now it's like, well, wait a minute. How did they get the experimentally measured value to match if it wasn't even the correct value? And they both independently did it? What? What? Oh no. They later admitted that after they did their calculations, there was some discrepancy. So they got together and sorted out the discrepancies and made them whole. That's the opposite of independently deriving. That's I would go as far as to call that cheating, right? Like that's crazy. So, and this is like, canonized in the mythology, right? So this is Feynman commenting on it. So he says that our mistake, this is them commenting on it. Where was the Feynman quote? It turns out to be the calculations. Anyway, they admit to it. Feynman commentates on it. So this is them just, admitting to what they did was physically meaningless, right? And to kind of give a representation of what they did here. So there was 5 Feynman diagrams that they said they solved. They wrote a 14-page paper. They were like, all right, boys, we got Feynman diagram 1 and 2A, and we got 2D. We got to really solve these. And then on page 8, they're like, okay, none of that was meaningful at all. It's all about 2E. And then he's like, all right, it's actually not about that either. It's all about 2C. And in the next paper, I'll show you how we solved it. And they never published that paper ever. And when you look at what gives the total value here, we can see that the most important and significant figure here is 2C. So the most meaningful diagram that they solve to give the combination of diagrams to give the energy output for the expected, to change the expected value to match the experimentally measured value comes from 2C, where at the end of their paper, they're like, yo, bro, we'll hit you on the back end on that derivation. And then they just never did. So that's very cool. So to kind of recap the history here, we have we're going from 1950 to 1989. We have them changing the, just dealing with equations that deal with infinities that have never been physically meaningfully solved, that aren't being, they're using coefficients and using things that aren't even derived as a consequence of quantum field theory, right? The theory that quantum electrodynamics is supposed to be supporting. It's just, so we can just see here that this is all just about the math, and it's not about actual meaningful interpretation of anything, right? So you are absolutely 100% free to interpret reality and these experiments and the molecular structure of everything how you want. Now this model has some benefits to it. It's easy to conceptualize. You can teach it to people, right? It is a model, man. Do not be confused and start thinking that anyone solved a Feynman diagram and this is meaningful, because actually we're going to look at a long history of nobody ever showing how they solved the Feynman diagrams in a meaningful way. And in modern times, what they do now is they use supercomputers to do it. And there's no source code available to show what renormalization techniques they're doing. They're just getting an output and they're like, oh my God, it matched. Like, yeah, I bet it sure did. It sure did, buddy. Right? All right. So now we're going to wrap up some of the easier concepts to grasp with quantum theory. So we're going to get into quantum entanglement, right? So this is the EPR paradox. This was put because we're all familiar with. Actually, let me back up a minute here. I started off by introducing the cast and crew, and I talked about Max Born in 1926, who put forward the idea that if you square Schrodinger's solution, or the solution to Schrodinger's wave equations, you can say that the electron exists in a probability of that squaring of the solution. And that is a philosophical interpretation. There's no experimental verification of that to be correct. That's just entirely, and he puts that forward in his paper. And then that leads into the Heisenberg, the Copenhagen interpretation, and that's put forward by the Heisenberg uncertainty principle, right? Where you can't measure the electron. Where does it exist? Well, it exists in the square of the solution to the wave equation, but we can't find it. And the more precisely we know its momentum, the less precisely we can know its physical location. So that's called the Copenhagen interpretation. And all of that comes out of Max Born's squaring that solution to the wave equation, to Schrodinger's wave equation, on philosophical grounds purely, right? So Einstein was having trouble with instantaneous action at a distance and timelines not requiring Lorentz symmetry, right? Because his theory is based on the principle of relativity of simultaneity, which states that there's no cohesive timelines. Everything has to be relative to something. So that's kind of what the Togonama guy was pointing out. He was like, "Yo, bro, you guys are doing great work over here, but I'm not seeing a lot of divergence from a reference frame from proper time or anything like that," right? So anyway, Einstein and the boys got together and mathematically debunked the uncertainty principle, right? So again, this is the Heisenberg uncertainty principle, and Max Born's squaring the solution to the wave equations is just philosophical, right? It's just math, right? The idea that you can't know where the electron is because when you go to try to measure it, you're going to bump it out of the way with the photon. So you can't measure it, right? It's just going to be in this cloud. So they actually go ahead and debunk that by showing that if you analyze the first, if you take a two-wave system, right, and you analyze the first wave equation, and then you use the entanglement math on it, you can actually identify all the properties from the second part of the system because they're entangled, without actually measuring the system or disturbing it, which would collapse the wave function and all that, right? Which is, we can't actually know, right? So it would just magically move. Well, they showed that that's not mathematically tenable and that you could work around that entirely. And there's no solution to this. This is called the EPR paradox, right? This is a rebuttal to quantum electrodynamics, essentially, right? Now they'll say, "Oh, relativity theory is proof of it," and all this stuff. Yeah, cool. That's cool, man. But anyway, Dirac tried to refute this, and there was no refutation to it. So he actually retired from QED off of this. And in an interview, he was like, "Yeah, this pretty much body bagged it for me." And Niels Bohr had to convince me to come back using the Compton effect, which we'll get to in a little bit here. And let's see. And then Heisenberg was going to refute it, and then he realized that he couldn't. So he backed out as well. And that was stated by Dirac, verbatim. So there's no refutation to it. And so the idea that we can't know and wave particle duality, collapse, wave function, none of that's real. So Dirac was, he literally, that was like the final straw for him. And then he came back over Compton scattering, which we'll get to later. Okay. So now we are at the part of the presentation where we need to switch to Shane. Shane, are you back, sir?
Yep.
Awesome. All right, everyone, please join Shane's stream for a moment. We're going to watch a couple of videos and talk about the implications therein, because a lot of this hinges on wave particle duality, right? So we're going to go over the double slit experiment, quantum eraser, the which way, which is the same thing. And then there's one more we're going to go over. I can't remember off the top of the dome, but we're going to hit them all. Oh, yeah. And then we're going to get into the new quantum thing that measured Earth rotation. And then we're going to cover neutrinos. Okay, so Shane.
Double slit first.
Let's see here. Let me pull you up and see what you got up. Yes. Okay. Skip to. Ooh, dang it! I don't have timestamps for that. I should have been more prepared. Give me 1 second. Because there's only a specific part we need to watch. All right, I'm not going to watch a YouTube ad. That's crazy. 1 second, lads.
How?
Okay, so this is a professor of quantum electrodynamics, and during the lockdown a couple of years ago, she did her own double slit experiment to test the wave particle duality that she believed in. And she was shocked to find that she had been, the way that they conceptualize the wave now, right? They conceptualize the wave as being the mathematical abstraction and everything is a particle, right? So she was like, actually, it's a wave the whole time. And that kind of blew me away because, the way that that's bad. That's the opposite of what I've been teaching, right? So Shane, if you could skip to 707.
Okay.
And then we'll let that play for, let's see, 937.
Gotcha.
Notice that at least some of the light falls on this spot. Now let's open both paths simultaneously, and the light just disappears from this spot. There is no way for Newton to explain this. Think about it. If you believe in the kind of particles that Newton did, then when just the left path is open, some of your particles will reach that spot. And when the right path is open, some of your particles will reach that spot. But when both of them are open, it's like the particles from the right side and the particles from the left side just happen to cancel each other out in this spot.
Yo, I'm going to go AFK for a second. Let this play for like a minute or two. I'll be back. I'll interject when I'm back.
Gotcha.
Which just doesn't make sense. But why not? Why can't you just have the particles cancel? Well, because in this spot, they need to cancel. But just a little bit over, the particles coming from the left and from the right should happily coincide. It's like they sometimes choose to cancel and sometimes they choose not to. So I'm sorry, Newton, but particles like yours really aren't good enough to explain how you could ever get cancelling. But then, how do waves manage to explain the double slit experiment?
Let's imagine a wave is coming out of the laser. On the right side, the wave encounters the hair, and because it's an obstacle, it bends and it spreads out like we discussed before. On the other side, the exact same thing happens. Back in our wave pool, the black obstruction in the middle now represents the hair. And as you can see, the waves on either side do spread out and they overlap. But something very surprising is happening in that overlap, and you can't really make it out in this precision setup, but it's going to be a lot more clear in the animation. Where are all these lines coming from? To understand what's going on, imagine you're on a boat in this spot.
Then the wave coming from the left will have its peak reach you at exactly the same time as the wave coming from the right. Together, they tend to push you up even higher. The troughs also meet you at the same time, so this spot is just really choppy. But if we instead move our boat to here, then the peak of the right wave hits exactly when the trough of the left wave hits you. The peak tries to move you upward, while the trough tries to pull you down. And so in the end, they cancel out and the boat doesn't really move up or down. So this spot is surprisingly calm. There are these choppy and calm spots all over, and if you map them out, then you get these lines. What's this got to do with the double slit experiment? Well, look.
Okay. So this diffraction pattern here that is predicted by wave or by light being a wave is what's measured, right? So when they do the double slit experiment, no one has ever seen the collapsed waveform where it would just be two slits of light, where it would be two particles, right? Essentially, instead they always see a diffraction pattern where the wave that's produced by the waves interfering with each other, where the peaks and valleys, intersect and all that, which creates the gaps that they see in the bright dots that they see, right? This is consistent with light being a wave the entire time. and then we'll get into some extra attempts here to collapse the wave function. But yeah, so a lot of people will say, okay, well, is this an experiment? Is this an observation, et cetera, et cetera? I would argue that it is an experiment because you're introducing the independent variable would be the slit, and then the configuration would be you manipulating that independent variable to change the dependent variable, which would be the diffraction pattern, right? And then the control would be your wavelength of light that you're using. So you can absolutely look at this as an experiment, and you can look at the quantum eraser experiment as an experiment as well, which we'll get into that, because there's a lot of confusion, it seems, where it's like, is it an experiment? Is it a demonstration? Does my consciousness alter the experiment? All this stuff. No. It's much simpler than all of that. So we'll just go ahead and demystify it with that. So that's for the double slit. That's what's measured. That's what she saw. Yep. Awesome, SC. Yeah. You know what? We're actually going to use that guy's video later, bro. If you know where that particular one came from. Actually, I think it's a red one. Maybe it's not his, but anyway.
That's mine, bro.
Oh, okay. Yeah. I was going to say, I think his was red. Never mind. But yeah, we're going to watch one.
It's all good. It's all good.
Yeah. We're going to watch one here in a second. That's badass. Okay. So I think that's all we need from her. You can check out her channel. She is Looking Glass Universe. Check her out on YouTube. Her video is, I did the double slit experiment at home. Very cool. And then let's see, what's next? Shane, what do we got next?
We got quantum mechanics is wrong or delayed choice quantum eraser girl.
Ooh, okay. One second. Let me pull it up so I can see. We got quantum mechanics is wrong. Decoherence. Yeah, decoherence. Yeah. Okay, if you could open up quantum mechanics is wrong and put it at 1651, that'd be great. Actually, take it back to 1549.
All right.
Thank you, sir.
So then how do you explain photons making this interference pattern?
So
it is because
pause real quick.
the
So yeah, he's explaining like the Steelman of how they're trying to explain, well, yeah, it's still a dual particle. So how do they explain it? Well, they're going to say that the photons go through both sides and they interfere with themselves. That's a great story. But maybe we can introduce another variable to see if we can collapse that wave function. So anyway, we'll go ahead and let him play out now that we're all caught up to speed.
Photons are in a quantum state superposition. And while in that state, a single photon can pass through both slits at the same exact time and interfere with itself. This allows us to see the photon particles in an interference pattern like this because it is in a quantum state superposition at this time. So if the photon's quantum state superposition were to decohere right now, then it would go back to the two blobs that we saw on the Dr. Quantum picture. As you can see, this is some of the quantum weirdness that people talk about. Sure, it's weird, but it's because it's wrong, not because this is how nature works. So from a particle perspective, you're looking at a fully cohered quantum state superposition of photons. What I'm going to do now is add more noise to this environment to try to decohere this quantum state superposition of photons. Now, why would I do this? This is why quantum computing is not working, is based upon noise in the environment. Quantum computers are not working because they are having trouble maintaining quantum state superposition. And their reasoning is because there is external noise in the environment that is decohering the superposition that they're trying to maintain inside these computers. So why am I able to maintain this quantum state superposition of photons?
All right, pause for a sec.
Okay,
so the double slit experiment is explained through what he was just explaining about superposition, how it could go through both slits at the same time and interfere with itself. Now, people will say, okay, well, what about the quantum eraser experiment? And then, well, actually, let me back up a second. No one's ever seen the pattern that corresponds to light being a particle where it would just be two blotches, right? It's always,
Yeah, it's just math.
yeah, it's always the diffraction pattern that you would expect for the wave. So this is all about trying to explain that. So what they're going to do now, we've already talked about how superposition and quantum entanglement isn't, even mathematically real, and that the idea that, you can't measure it because in wave collapsing and all that now isn't true. And the reason that what he did there with that heat gun, as he was explaining, was he was introducing, ambient noise to the background, that would collapse the wave function. So they say in quantum computing, where instead of using a regular, on-off switch to do computation, they have they're maintaining a superposition of on and off at the same time. And because of that, they're able to calculate things faster because, it's got all the states at once. It's like on, off, on, off, all that. So anyway, all the iterations you could have. So to maintain that, they say, okay, we have to keep it at 0 Kelvin. We got to keep it real cold. If there's any temperature deviation from 0, then our, what do they call it? A qubit transistor or something like that will, it fails because we lose the superposition, right? Okay, cool. So if you can't quantum compute because you can collapse a wave function, right, because of ambient temperature, then when you introduce a heat gun to the double slit experiment, you should be able to see that particle, right? You should be able to see that particle pattern, and there's nothing, right? It did nothing.
That explains the heat gun. Okay, that makes sense. Yeah.
Yep. So yeah, that's why he did that. It shows that because like the effects that they're because by the way, so let's go over quantum computing real quick. It's been a complete failure of an industry. It's falsely propped up. You can look online now. Many places are abandoning it and realizing it's a failure, et cetera. And then other places are just fresh to the journey because they're just getting a fresh injection of quantum money from your friendly government bank or whatever gives them money. But anyway, what they do is they generate a large data set and then they just pull from it using a random number generator. And they're like, look, boys, we just quantum computed. And that's actually, nothing in terms of the way that they're trying to get us to conceptualize the meaningfulness of this, as if they've calculated they could crack a hash by simulating all the possible solutions at once. Like, nope, that's not
You
what
mean like hacking on TV. Like, hold on, quantum computing.
Right. It's not that at all. It's literally just a random number generator. The biggest paper published by Google a couple years ago, I think it was 2017, I want to say, you can read all about it's a very beautiful PDF, right? You can scroll through it and read all the references and terminology. But what they're doing in that is that they're just pulling a data set out of a large sample that they generated, and it has nothing to do with the idea that how they want us to conceptualize quantum computing. So anyway, that just falsifies the idea that it's that the photon and all this travels as a quantized packet and all that. So we can move on from that one. Give me 1 second. Let me see who's next. I think Quantum Eraser is next. So we'll hit up our girl Sabine. Can you pull up the German?
Our girl.
A lot of you have asked me to do a video about the delayed choice quantum eraser.
Okay, so her accent's a little strong for playing it at an increased speed, but she gets to it rather early in it. So we'll just watch it here for a couple minutes here. But yeah, she spills the beans. Go ahead.
It's the past. I haven't done that simply because there are already lots of videos about it. For example, Matt from PBS Spacetime, the always amazing Joe Scott, and recently also John Lincoln from Fermilab. And how many videos do you really need about the same thing if that thing isn't a kitten in a box? However, having watched all those gentlemen's videos about quantum erasing, I think they're all wrong. The quantum eraser isn't remotely as weird as you think, doesn't actually erase anything, and certainly doesn't rewrite the past. And that's what we'll talk about today.
All right, you can skip this intro part. Just like fast forward a little bit. Oh, never mind. She already did it. Oh, my bad. It was really quick. Sorry, this is the important part.
Years old quantum mechanics.
No, just back up. My bad.
Let's start
It's like
with a
1
puzzle
second,
that
1
has
second.
Yeah, my bad.
quantum mechanics. Peter's 46 years old and he's captain of a container ship. He ships goods between two places that are 100 kilometers apart. Let's call them A and B. He starts his round trip at A with the ship only half full. 3/4 of the way to B, he adds more containers to fill the ship, which slows him down by a factor of 2. On the return trip, his ship is empty. How old is the captain? If you don't know the answer, let's rewind this question to the beginning. Peter's 46 years old and he's captain of a container ship. Peter's 46 years old. The answer's right there. Everything I told you after that was completely unnecessary and just there to confuse you. The quantum eraser is a puzzle just like this. The quantum eraser is an experiment that combines two quantum effects, interference and entanglement. Interference of quantum particles can itself be tested by the double-slit experiment. For the double-slit experiment, you shoot a coherent beam of particles at a plate with two thin openings. That's the double-slit. On the screen behind it, you then observe several lines, usually 5 or 7, but not 2. This is an interference pattern created by overlapping waves. When a crest meets a trough, the waves cancel and that makes a dark spot on the screen. When crest meets crest, they add up and that makes a bright spot. The amazing thing about the double slit is that you get this pattern even if you let only one particle at a time pass through the slits. This means that even single particles act like waves. We therefore describe quantum particles with a wave function usually denoted psi. The interesting thing about the double slit experiment is that if you measure which slit the particles go through, the interference pattern disappears. Instead, the particles behave like particles again and you get two blobs, one from each of the slits. Well, actually you don't, though you've almost certainly seen that elsewhere. Just because you know which slit the wave function goes through doesn't mean it stops being a wave function. It's just no longer a wave function going through two slits. It's now a wave function going through only one slit, so you get a one-slit diffraction pattern. What's that? That's also an interference pattern, but a fuzzier one, and indeed looks mostly like a blob, but a very blurry blob. And if you add the blobs from the two individual slits, they'll overlap and still pretty much look like one blob. Not, as you see in many videos, two cleanly separated ones. You may think this is nitpicking, but it'll be relevant to understanding the quantum.
Oh, okay, yeah, sorry, go ahead. Never mind. She's about to get to it.
Eraser, so
That's why
keep
you
this
said
in
we never
mind.
get that.
It's not so relevant for the double slit experiment because regardless of whether you think it's one blob or two, the sum of the images from both separate slits is not the image you get from both slits together. The double slit experiment therefore shows that in quantum mechanics, on what you measure.
648.
Yes, it could be detectors and then just
okay.
The semi-transparent one is a B.
Okay. So what they do there for the quantum eraser experiment is that they try and come up with a configuration where they introduce a slit that will block off a path to one of the detectors, so you don't know which one it'll hit. And so there's two possible solutions. Now, what she was just explaining about how when you recombine the pattern from a single slit, when you overlay it with the other one, it makes the full diffraction pattern that you would normally expect. So all they've done with the quantum eraser experiment is split the two readings up, and then they present you with the single halves of it, and you're like, oh my god, dude, I looked at it and my consciousness made it go backwards in time, and no, none of that. None of that happened at all. It's just the same thing, just you're looking at it split in half. So that's super unfortunate for them because it's not a real phenomenon. It's literally just mysticism that's presented as an actual experiment. This is physically meaningless. It goes nowhere. Nothing's ever come out of this interpretation other than philosophy that holds together the a belief in the mathematics that hides the fact that there are continuous lines of force facilitated by a fluid medium, and everything is connected in that medium and not infinitely disconnected and represented by discrete quantized packets of discontinued energy. Okay, so I think that's it for the main ones regarding quantum entanglement and all that. And I think we can get back to my screen.
Do we even watch it?
What's that?
I think you said go to 640.
No. We just need the diagram. She already gave the gravy.
Oh, okay.
Yeah, we're good. So shout out to Sabine for spilling the beans on how that works. All right, cool. So now we've been through all the videos, we've entangled. So now we're on to neutrinos. Cool. So neutrinos, they say there's a we exist in an infinite sea of neutrinos, right? But they only, and all these stars exist, all the infinite distances away and what have you, but they've been emitting light for, infinity or whatever. So we should have a sea of neutrinos coming from them, but they say that primarily most of the neutrinos that they quote unquote measure come from the sun. And they say that they don't interact with anything. They have no mass. They have no charge. They don't do anything. And they came up with an experiment where they could detect them, and they got a measurement, and they were like, oh, look, neutrinos, boys. 1 second. Let me pull up the actual slide for it.
Why did they say neutrinos don't come from stars?
There's no actual answer. They should, though, because of the nuclear processes involved in the, and how they say that our star works. Well, all the stars should be emitting a sea of neutrinos that should be encompassing all of us. They say that we're only getting the neutrinos from the sun, and it's hard to detect those because of reasons.
Don't they say they have extremely low mass, or did they change it again?
So they say that they have no mass, no charge, no properties whatsoever, and the only thing that they have is a 1/2 nuclear spin that's used to justify a problem that Wolfgang Pauli was having regarding the and the other issue that they have with that, right? So they use a neutrino interaction to describe Cherenkov radiation, and the problem with that is they're introducing this thing that has no charge, and they're saying that somehow it's interacting and producing radiation, which violates the conservation laws, and no one bats an eye at that, right? That's just some on the free full DS.
Yeah, it's a free parameter concept.
Yeah, so it's like literally nothing. And then so they say, well, it doesn't interact with anything, but we're in a sea of them. But when we went to do our experiment to measure them, our detector actually, one of them interacted with an electron in our detector. So the smallest possible thing that you could ever imagine, it interacted with it, and that's what gave them their detection. So that's very cool. That's, seems statistically viable or whatever. Oops, I got the wrong slide up. 1 second. Where is, no, should be, there we go.
Well, it would have to be. I was going to say that because don't they have a picture of the sun through the earth, a neutrino picture? So they got to make up their minds. Yeah.
They were telling me the other day that neutrinos come off of everything that's subject to some kind of decay or radioactive decay or something. So, like, they were saying neutrinos come off rocks.
Yeah, so every 15 minutes or something, there's, due to radioactive decay or beta decay, there's they emit neutrinos or whatever, but can't detect them. Oh, and then they get into the oscillating neutrinos, which is where they had a prediction for how much energy they should be measuring using their oscillating neutrino detector. And when they took their measurements, they got, 40% of the value of the expected value. So they said that that's actually proof of their conceptualization of oscillating neutrinos, because in their model, while the neutrinos are in transit from the sun to the earth, they can change families and become a different type of neutrino that their special neutrino detector can't detect. And they actually predict that 60% of the neutrinos in transit will turn into a different family flavor. And that means that their 40% energy reading spike that they got on their oscilloscope definitely means that the sun is emitting neutrinos. So that's really cool that they were able to do
change
that.
in the upper atmosphere, I think, right? When they encounter.
They from any time between the infinite vacuum of space that's known as space, they can change. Yeah, they can just become a different thing here. So
you need them to be.
So a quick word on Ubler's paradox for those who aren't familiar. I thought this was really funny. Totally forgot about this. So Ubler's paradox is that if all the stars are these massive giant burning balls of light and everything's a parallel light ray, how come when everything we see in the sky should just be a giant parallel light ray and we shouldn't really have a night sky? It should be kind of milky white. And there's no solution to that, no answer for that. And what they came up with to finally answer it was Hubble's the Hubble constant, right? So the expansion of the universe. So if the if the universe wasn't expanding at 4 times the speed of light, you wouldn't see little dots in the sky. You would see a giant coherent beam, a giant omnidirectional milky sky, of nothing that you could discern anything from. So shout out to your boy Ubler, who realized that back in the day, 1826. And let's see here.
I like that paradox.
Dude,
that paradox. They got out of it with dark energy, though. Yeah,
it's a classic, bro. And it's like, well, they're teetering on, oh man, maybe Hubble constant's wrong. Maybe it's not expanding. Did the Hubble telescope falsify the Big Bang? No, guys, they have nowhere to go from here. Literally, their conceptualization of starlight is that there's an infinitely sized parallel beam that should be headed to you from infinity. And the only thing that's stopping that and giving us the ability to see them as discrete dots in the sky is the fact that there's an infinite separation between them that's happening 4 times the speed of light. So never forget that. So now we're going to get into Earth rotation and measuring ether wind and quantum effects regarding what's it called? Earth rotation, right? So there was a paper recently. Where did I have it? Do I have it up? Oh, yeah, I do. Awesome. Can you guys see this? Yeah. Did it change screens?
Nice.
Oh, is it up? Hello?
Yes.
Oh, okay. Sorry. Didn't hear you. Okay, cool. So they get into this new thing, this experimental observation of Earth rotation with quantum entanglement. Okay, so what we just learned is that quantum entanglement, quantum superposition, all these things are not actual real processes. Everything's just a wave. So when they talk about this being a quantum effect, that's not it at all. It's just this is a regular interferometer, right? So this idea of we have to maintain a low quantum decoherence. Oh, really? You mean like if you were to put a heat gun on the laser beam, it would turn into a part? Nope, never been observed, never been done. So this is literally just an interferometer, boys. So nothing special here. Now, to get back on just a quick recap on Earth rotation and measuring that with a single axis gyroscope, because when you look at the pictures for this paper, actually, do they show yeah, they do. They have some nice diagrams in here. So we have this closed loop circuit here of a fiber, right?
Oh, we're looking at magnetic stuff, dude.
Now get divergence convergence slide up.
Ooh, one sec. Oh, I know why. Hold on. Thank you.
You are partying by yourself.
Yep. I just realized what's going on. So
I just found a complaint to file with Stone. So hold on. I'll
change
be right back.
screen 1. Now we're good. Now you should see the paper.
Yep.
Right. Okay. Sorry about that, boys. Thank you, Stone. So this was recently put forward as proof of Earth rotation, experimental observation of Earth rotation within quantum entanglement. Very cool. But as we just read and reviewed, that there's no such thing as quantum entanglement, and you can't decohere a wave into a particle. So that's not a real hurdle to overcome. And this is just an interferometer, right? Just a standard fiber optic interferometer. So what they've got here is they've got a closed loop circuit, combines to a detector. It's orientated 45 degrees off axis relative to its parallel. Oh, no way. It appears to be at the 45th, like all the other ones in the north. Nice. Shout out to your boy. Cool. So what does that mean for the Earth? Is it a globe? Is it flat? Because the reason that this has to be tilted at this is such a good diagram. The reason this has to be tilted at the 45th, right, is because it has to be aligned with the axis of Earth's rotation, right? Very mysterious. And otherwise, this would not get the proper reading to measure the 15 degrees per hour, right? Remember thanking Bob? Everyone get a thank Bob in there?
I remember.
Cool. So here we're going to look at another presentation now. We're going to deviate off of that and just kind of look at the orientation of the single axis gyros to kind of recap and, go into detail here. So we got the interferometer and the ways that it should be aligned at the respective latitudes if we're on a globe. And we have the YouTube channel Plenum88. Highly recommend you check out his YouTube channel. He has awesome videos and experiments that he does. Oh, this butchered my formatting when it got converted. But anyway, here's his homemade apparatus here with a fiber that he did himself, closed loop, orientated 45 degrees. And then his location is, real quick, here's another one. Here's the Ginger project. This is bringing general relativity into gyroscopes deep in an underground basement where we can only measure the annual notation and perturbations of the moon and all this stuff, and sidereal rotation and what have you. So that's very cool, and we'll get into how they measure that here in a second. But the significance here is in the tilt angle again, right? Because if you're not tilting with Earth's rotation axis, then you're not going to get these readings. So your boy was, the Ginger lads are over in Pisa, and they're right around the 45th. Our boys over here, this is another part of the Ginger project. These guys are in Germany. They're at the 49th, and then our guy here from Canada, right here from Toronto, he's at the 43rd. And let's see here. So this explains the correction angle. Then they're like, okay, well, must be a globe. And what we have here is an ether vortex, right? That will give variance in the speed of light relative to the latitude as you move further away from the vortex. Now, for fully conceptualized are these rotation angles on a flat Earth, right? And then if there's a vortex, right, this is what those correction angles are going to look like. So we actually absorb all the globular correction angles. So these are no longer mutually exclusive to the globe. If you believe in a flat Earth with the ether field, that follows a toroidal field, right? So in the northern hemisphere, you're going to have that inner donut of the toroidal field that's going to produce an east-west bias, and then moving outward, you're going to have a west-to-east bias by the outer toroid, and all these angles to get the 15 degree per hour to correspond to that sidereal rotation are going to be the exact same. And this was modeled out by an old friend of mine. You could check his YouTube channel out. It's I Can Science That. He is a globe earther. He does not believe in the ether. He did this as a generosity to me and was just seeing if it would work and how to conceptualize it, because I'm all about that ether vortex. So he put together a little conceptualized model to kind of show if my hypothesis about ether following the toroidal field would represent these angles, and it did. So that's very cool. So to kind of give an overview here, we have the sky above us, the cosmic microwave background being aligned with the sun's ecliptic. We have the sun doing its analemma over top of us, following that CMB, that rotation of the sky. We got all these, we have measurements of sidereal rotation. So let's get into what they're actually measuring here, right? Because it's like we got this device here. What are these measurements? There's a little quantum effect, they said. Well, no, there's just an interference pattern, right? That's all there's ever been. So it's the same interference pattern that they're looking at. And then they're plotting the fluctuations within that pattern on a graph against sidereal time. And when they plot those minimum and maximum dimensions against sidereal time, right? They're corresponding that to being evidence that, okay, this is when the Earth is rotating into the plane of motion of, what's it called? As we're going around the sun, sorry. So, and you get a little variance, right? And then because we're in this direction, blah, 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 that's when you're going to get the Galilean velocity addition, and that's going to make your fringes move a little bit, right? So that's what they're reading. It's not like they have a special, the red circles are, I did mute you for a second. The circles are the orientations of the gyroscope. So when we're looking at the correction angles here, this is the orientation of what it would be on that other model here, which is shown here. So that's what that's showing. So, All right. Think we're good on that. Let's explain the measurements. Let me double check before we move on. So yeah, this is kind of how I conceptualize the ether and how it follows the Earth's toroidal field, and then the measurements that there's daily fluctuations and annual where the fringes will reach their minimum and maximum peaks. That's what Miller was measuring. That's what Michelson Gale Pearson is. That's what they've always measured. That's what any Earth rotation measurement is. That's what it's always been. And the fluctuations, now the reason that they don't like the translational speed and they divide it interferometry into linear and angular is because the translational speeds, if you were to equate those that they're measuring for the 15 degrees per hour, they would fluctuate by thousands of kilometers an hour. And that's way outside the scope of Earth rotation, right? The Earth can only be rotating at the same speed, essentially, right? It can't drastically move faster and slower multiple times throughout the day. So that's why they can't use the translational measurements to relate to, like, okay, this is a 30 kilometers a second measurement, et cetera, et cetera. That's why they break it down into deviations of fringe displacement plotted against sidereal time, right? So conclusions. Is quantum electrodynamics and quantum field theory the correct interpretation of reality? Do discrete discontinuous discrete packets of energy make sense to you? And, so that's really all I have to offer. We're just looking at a series of renormalizations to reify what they've already assumed to be true. And it can't ever be falsified because when you get an experiment, they literally go, oh, no way, new value. Let's retroactively change the way we calculate everything and then go from there. So when you have that kind of freedom, you're not going to falsify anything. No one's going to come through and debunk anything. Where's your Nobel Prize? No one's ever going to get one, dog. They already gave one to the lads who made sure that there could only be one interpretation of this. And you should definitely never consider an ether, because if you have a fluid medium that everything is relative to, anything in that space would be relative to it, and you could measure the velocity of it, and you could prove Earth's velocity definitively, and that would cause a lot of problems because you would have to explain why you can't measure Earth's velocity, right? So that's it. If there's any questions, comments, concerns, we can free to hear them all now.
Nice.
And then my bad. I did mute you earlier, Vardak, but you're unmuted now. I was in the middle of something and I was like, I'm just plowing through.
Yeah, that was my fault.
You're straight, bro.
On the ether part. So is there an ether then? Do you think? And if so, where is it?
Yes.
I know, right?
I mean, it's the most indirectly verified energetic background conducive satellite.
It's like if there was a way, if there was a way to, if light measure. Okay, so this is the other thing with these measurements, right?
Just asking his opinion. I mean,
no, you're good, bro. Yes, I believe in the ether, and the way that we could substantiate this with an ether model, right? We could say, okay, if there's an ether and the source of these measurements is the rotating Earth, or if it's a rotating ether vortex, then if you get closer to the sky, then the fringes will increase, right? You'll get a faster velocity, right? Because you'll get closer to the source of motion, and there'll be a material medium that's influencing that, right? So you're looking at a velocity gradient coming down from the sky. So that's what Miller's work was about. He did measurements at different elevations and found that the speed does increase at altitude. And then that was further corroborated by Yuri Galev in 2004, where he did radio interferometry of the optical wavelength, so you could see interference patterns. And then on top of that, that was actually two-part, where he was testing the hydrodynamic nature of light, where he was basically orientating the apparatus, a half-covered interferometer, such that it would be aligned or parallel and perpendicular to the assumed flow of ether. And what he found was that the wave bands, when he rotated the device and to be parallel and perpendicular to it, that the wave bands would produce a chaotic pattern, right? And then it would become coherent after a certain amount of time, like the deviations from when it was from when it would recohere, being parallel or perpendicular to the flow, it would correspond to like, a laminar and turbulent flow essentially, right? So he was measuring the kinematic viscosity of the ether through the displacement of the wave bands relative to how long it took them to settle and then become coherent. And then within that, he also measured the same periodicity that Miller measured, right? So those same fluctuations that they say are Earth rotation that measure that when they plot against sidereal time, et cetera, that they say are mutually exclusive to a closed loop interferometer. Yeah, your boy straight measured that with a regular interferometer. Actually, I'm sorry, his was closed loop. And then he did radio signals back and forth. Now the radio signals back and forth were actually one ways. So we had one going downhill and one going uphill. So we had two data sets to plot against, and they were symmetrical in the periodicity measured. So 30 years later, this dude measured the same periodicity that Miller was measuring in 1905 to 1925. And in addition to that, he plotted out the velocity gradient for the speeds. So yeah, there was a ton of that with his work. So yeah, I totally like this. Like, so here's the thing: if there's no ether, right? If you take an interferometer to altitude and it's measuring Earth rotation, so it's measuring a fixed point in absolute space that the rotation is relative to. It's not going to change, right? It's not going to measure periodicities of other things and all that, right? So the only explanation that would explain that is if there's an ether that's in motion and it's measuring that, right? Now, when you get into the history of interferometry and you start with Fazal and Fresnel, they had their prediction for, actually, I'll pull this up now because I have slides for it. One second.
Wait, so when I'm looking at the sky and measuring the sky, I'm not measuring the Earth. I am, in fact, measuring the sky. Interesting.
Yeah. Okay, so Fazal, right, they had the induction rate of light. So to start us off, it's like, how did they get to the speed of light? Is that a real number? Is that debunked? Is that just nonsense? What does that mean? Well, so they started off with Faraday and Maxwell's equations, right, for how they could derive the speed in a vacuum, and that, substantiated experimentally by Faraday's work. And then we have another experiment where they count the induction rate by mirror flashes. So they have a coherent beam, a gear a toothed gear that spins at a constant rate, and then they count how many mirror flashes they get over a period over, I think it was 20 minutes actually. So, and then doing that and averaging it out, they found that everything was in alignment with, Maxwell's equations, and they were, making solid predictions. And then from that, they took it to the next level and started doing interferometry here. So what they have for the Fresnel drag experiment, and this is why I believe, oh, thank you, Shane. That's an awesome, yeah, there's that vertical gradient, dog, that vertical velocity gradient to the sky. So I'll pull that up here for the boys in a second. So Fresnel drag, so using sunlight and half split mirrors, half crystal mirrors, and then recombining the beams and then having water go through a tube that will make the light go with or against the translational movement of the water. They measured a 44% velocity relationship to the speed of water going with and against. So 88% in total, 44% with, 44% against. And then that's obviously in conjunction with the refractive index of the water itself, right? So this is outside of the confines of the refractive index. There should be no further displacement. And the hypothesis here was that the ether was a material medium in which light propagated through, and that if you had a moving material media, the Galilean velocity addition would apply, and you would add the speed of light plus the velocity of the water, and that would give you your predicted fringe patterns, right? And that's actually what they measured, right? So they fully substantiated their hypothesis of the ether being a material media that will be dragged in proportional to that velocity. Now, obviously, with refraction, you're not going to get the full velocity, but that's where Oliver Lodge and another guy came in around 1910, 1912, and they started doing rotating interferometers, right? They made smaller versions of this that would rotate on a table. Let me actually, I have a Sagnac slide. Sagnac. So what they started hypothesizing here was, well, actually, before we get to Sagnac, right, what they did is they took Imagine this setup here, right? And then instead of having a closed loop, or instead of nothing to propagate through, imagine a series of crystals lined up, like a row of crystals. And then they rotated the interferometer, the light's propagating through the crystals. So instead of water this time, it's propagating through stationary crystals that are, well, they're rotating with the interferometer, but otherwise stationary, right? So what they did is they measured, again, the proportional velocity to the rotation of the device, and then that refraction index, obviously, of the crystals. So that's when SAGNet came along and was like, yo, if we do this without any medium, I hypothesize that there will be an ether vortex of the apparatus itself, and it'll produce a proportional fringe to the rotation of this device, even without a material media to drag it. And what do you know? Your boy measured it exactly proportional to the rotation of the device. So that was in 1913. So that's when he was like, okay, there's a ether vortex. That's where all that comes from. Because his conceptualization of it was that the Earth was encased in an ether vortex that would be like an atmosphere, and then within that you would have rotation or motion, and that would produce its own vortex within that, and that would be where you would get your measurement from. All right, so that was a little bit on the history of interferometry and why I believe in the ether, because it's fully substantiated and you can measure relative motion to it, right? So this went on in 2004 with Ruyang Wang, where he showed that you could measure linear motion, right? Because this whole thing was about measuring linear motion of the Earth through the sky. And they found that, they couldn't do it. So they said, it turns out you can't measure relative motion, and that there is no ether to measure the motion to, and nothing's at absolute rest. Everything's relative to something else, blah, 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 and all this, right? None of that's true. And they've always consistently made measurements with respect to absolute space. And Wang showed that in 2004 with the linear interferometer configuration. Did I add the Wang slides? No, I did not, but do have Wang in here somewhere. Let's see if we can find him. No, don't have. Wait, is this it? Maybe no. Nope. Okay, no worries. But yeah, that's why I believe in it. You can measure the sky rotating with it, and it rotates faster when you get closer to the sky.
It was a very detailed answer, man. I appreciate it.
Yeah, no worries, man. No worries.
It's like I might have been asked once or twice before.
No worries. Yeah. So yeah, there's actually a guy named Matthew Koski who came up with it, who has an ether model that the Galev guy references a lot. So let me see if I can find. Actually, it's in the beginning, the ether hypothesis, because I take a lot of his model because I like what he put forward, and the measurements align with it, so it makes sense of how he conceptualized it. So he thinks that the ether is a gaseous medium that produces little vortexes. Let's see if I can find it.
Gaseous medium?
Yep.
No, go.
Let's see. Oh, here we go. Nope, that's not it. Dang it. Oh, here's me. Oh, here. Well, here's your boy Maxwell's equations, right? So we have nu equals 1 over the square of epsilon times mu equals c, right? So what do we have here? We have the electric permittivity and magnetic permeability in a vacuum, and nu over here, this thing that looks like a V, stands for vibrations, right? How many vibrations per second? And this equal sign is C, right? So this is the induction rate of light. So the 300 oscillations per second in a vacuum is equivalent to the quote unquote propagation rate of C. It's an induction rate, but this is how fast light can be inducted, and it's in a medium of a vacuum, right? So that's so some people will be like, oh, Maxwell's equations are debunked, or the speed of light. I don't know. They say a bunch of different stuff, but anyway, it's all derived from this, and then assuming a medium, right? Because what's this vibrating in? What's it perturbating in? What's this epsilon? What's this impedance, right? This is the impedance of the vacuum, right? What's causing the oscillation rate to be fixed at 300,000 oscillations a second, right? Let's see what else we got. Here we go.
Which nothing is stopping you consistently.
Here we go. So for the ether model from Matsutovsky, right, the anisotropy effect where we have the so that they say that light is isotropic, that it has no preferred direction. You can shoot it east, west, north, south, and there's not going to be any reading except for Michelson, Gale, Pearson, or anytime they try to measure Earth rotation. Then it's relative to the latitude, and it's actually never measured at sea. But for all intents and purposes, trust us, it's sea in every direction. So anyway, the Atsutovsky model predicts that it will be anisotropic, meaning that it'll have a preferred direction. So that preferred direction will be, it'll be faster east, or going from west to east than it is going from east to west. And that's, substantiated in the fringe patterns that they use to measure quote unquote Earth rotation. So we're good on that. We have a preferred direction, east to west. When light propagates north to south, there's no deviation. This is shown in GPS as well. There's corrections for the quote unquote Sagnac effect, but there's nothing that they correct for when the propagation is north-south. So then we have the height effect, which would be that when you go to altitude, the fringes increase, the speed increases, right? Because you're getting closer to the source of the motion. Then we have the space effect, and this is going to be where you measure that periodicity, right? So I keep talking about a periodicity, a fluctuation that's measured throughout the day where the speed of light reaches minimum and maximum dimensions. So what that means is throughout the day, when you measure the speed of light, it's not going to be 300 kilometers a second. It's going to be 300 kilometers a second plus 1, or 300 kilometers a second plus 2, that sort of thing, right? Or it'll be 299 million, like that, right? Or it'll be plus or minus. So then that's going to allow them to plot a graph against sidereal time where they have minimum and maximum dimensions, where they establish, okay, the reason that these minimum and maximum dimensions occurred is because Earth rotate, right? And if they increase at altitude, then that means that the measurement is not with respect to Earth's rotation. It's not with respect to the center of a fixed finite point at the center of Earth or anything like that, right? It shows that the causal mechanism of the displacement is the sky and in ether, and a translation of motion from the sky is how I would word it. And then the hydrodynamic effect, which is what I talked about earlier, where he was using the optical wave bands in a half shielded interferometer, where it would be aligned parallel and perpendicular to that east-west flow. And then how he was showing that the predictions, like the equations that he was using to make the predictions for the waveband displacement and how fast it would settle and become coherent again, were based off of hydrodynamic equations and the laws of hydrodynamics, etc. So basically he was just, applying hydrodynamics to light and found that it's applicable. All right. So that's the model that I subscribe to, right? And that's why when they do these measurements on the ground in a lab, right, when they got your boy here tucked away in a nice little lab at the basement, they're like, Earth rotate. We measure Earth rotate. But you put this in a hot air balloon, you take this to altitude, you start doing this in other locations, you're going to get stronger readings. And that's going to directly contradict it being the causal mechanism being Earth rotation. All right, cool. Any other questions, comments, or concerns? Thank you for letting me talk for such a long period of time. I appreciate everyone listening through that. But hopefully it makes sense.
All good, bro.
Yeah, that was awesome, dude. That was awesome, Alan. Thank you.
Yep, thank you. All right, cool. Well, I'll go ahead and close these out.
Can you do it again tomorrow?
Yes. Absolutely. Oh yeah, we talked about Compton scattering. We didn't get to it. So I came across a physicist on CERN through Flat Earth Fridays. Shout out to the boys on Flat Earth Fridays. And he put forward the Compton scattering as proof of the correctness of quantum field theory and relativity theory, because they're intertwined, because quantum field theory is dependent on the conceptualization of the photon, which is how Einstein describes how electromagnetic propagation works, which is basically through little discrete packets of energy that are related to Planck's constant, right? So we'll get into how that works here in a second. If you guys don't mind, if you want me to tap out now, we could wrap up, but if not, I could knock this out in like 10, awesome, 10 20. Okay.
Into this a little, bro. Please go. Please do, man.
Okay, cool. So let me bring this up. Present.
And real quick, I'll say that because we've been misled. We got some incomplete information in the past from other, and that's why this is important to hear the facts, the whole story, right?
Yeah, for sure. Yeah, so to start us off, my boy Ruyong Wang says, let's not judge a thing on its appearance. Instead, let us try to grasp its essence, right? Because quantum mechanics is a very complicated subject, as they tell us, right? So let's try and understand it at a base level, right? So the classical theory is that this line represents a continuous line of force, and quantum field theory wants us to believe that everything is little discrete packets represented by the discontinued dots there, right? That aren't representative of a line of force or indicative of a medium or anything like that, right? Don't you go thinking there's a medium in there, boy. All right. So, and then that obviously leads us to Maxwell's equations where the medium's inherently implied. So that's very cool. All right. So let's see, to get into the wavelengths and all that. So the distance between the peaks and the troughs for the wavelengths, and then what they have is that they say, or not what they say, but what they're measuring with electromagnetic radiation is they're measuring how they say it works is they have an electric field and they've generated a charge, and that electric charge as it's accelerating, it gains a magnetic field, and as that magnetic field goes to die, it reinduces the electric field, and then when that electric field goes to die, it reinduces the magnetic field, and it just keeps it going. So that's, and now you see here the way that this wave works for the electric. Oh yeah, so the magnetic field goes orthogonal to the electric field, following the right hand rule. So what we're looking at here would be, let's see, I just lost it. Dang it. I can't remember, but anyway, that's what we're looking at for. Oh yeah, sorry, this intersection point here. So you notice here that there's a little intersection point. So this would be when this field starts to die and then it reinduces the other one, right? With no charged particle in between. Now, this was they represent this nowadays by Maxwell's displacement current, where they say that, this is where they get to tell this story about how the electric field self-induces the magnetic field, even though that's never been experimentally shown. And it's just a mathematical term that's added so that they can tell the story of an accelerating nothingness keeping the charge going. But what's actually happening here is this intersection point here is the ether, right? So this is the that's it. Anyway, so now we get into the probability cloud for the electron. So here's a nice little graphic for that, where they say that the electrons exist. And then we went over the history earlier in the other presentation of how they quantified how they quantified this into a little particle, right? A little elastic billiard ball. And we get into E equals HF. Okay, so this is where Einstein conceptualizes the photon using Planck's constant for E equals HF. And what he's saying here is Planck's constant is how much energy can exist over a period of 1 second of time. In this equation, because it has no time either, and it's just bound to the frequency. So energy is equal to Planck's constant times the frequency, and the frequency of electromagnetic propagation is 300 million oscillations per second. That's the quick figure I give to round it off. But so what he's saying here is that the energy that can exist over 1 second emitted from a black body, so radiation, electromagnetic radiation, the maximum amount of energy that can exist times that frequency is proportional to the energy, and it fits over 1 second. So like that equation too. There's no time variable over here. So the default is also 1 second. All right. So that's why that works out nicely. It makes some nice predictions, but it also makes the wrong predictions because of that time thing. It's known as the quantum flaw. We'll touch on that on the back end. But the important part here is this is how we're getting the discrete packets and how we're breaking up the wave into little packets of energy, right? So the frequency, right? The wave energy, right? This line of force, right? This wave would be, instead of being a continuous line of force, it would be discrete particles here, and the amount of particles would be proportional to that vibration rate. So you would look at it like that. So that's how you would turn discrete, or that's how you would turn a continuous line of force into discrete packets of energy. And this is how they quantize it. So when they talk about quantizing the photon and all that, this is what that means. It's just making the energy proportional to the highest amount of energy that can exist over the course of 1 second. And that was measured by Max Planck in 1901, doing some black body radiation experiments using, what's the word I'm looking for? What's that thing? Graphite. Using graphite and doing black body experiments with that. So his equation fit that 1 second data set. So he solved for that curve. And that's where Planck's constant comes from. And now Einstein said, hey, E equals HV, boys. And everyone was like, oh, no way. So here we have Planck solving that for that constant and all this, or to put that H to work. So he's got his 1 second experimental value for the data set. And then he, shows that proportional relationship. So there's our E equals HV. Here's Planck showing it's proportional. And then this all goes back to the 1 second quantum flaw thing that we'll talk about a little later. But this is just Planck deriving it here at the end of his 1901 paper. And then, just 1 second of the data, just showing that there. And then, so let's see. So here's Einstein on the general cathode ray illumination of solid bodies. And here he's saying that the quanta of energy, and he's describing the photon exciting the light, consists of energy quanta of energy, which is R over N times beta nu. And when you get to what this actually means and you undecipher that, it's, spoiler alert, E equals HV. I'm not going to scroll all the way up to go back to it, but it's E equals HV. Let's see. And then here's our boy Max Born, right, coming in 1926, saying if one translates the results into terms of particles, one interpretation is that you can possibly use of Schrodinger's wave equations represented here. Gives the probability for the electron. So earlier when I was talking about how Max Born proposed this as a philosophical conjecture of what you can do mathematically to represent where the location of this electron exists in the wave equation, right? So you know how that lady was like, "Oh, dude, I thought the wave was the abstract part." She literally thought that the thing that gives the solution to the equation is the abstract part, not the squaring of the solution to be the thing that they can never find. But, so like that's the reversing of the abstraction, right? Like that's the inversion of where we're at with this and why it's so backwards. So we'll move on here. So he says, he's inclined to give up on the world of determinism of atoms. So you can't determine anything if you want to believe in quantum field theory or in QED, because, if you go to measure it, you're going to knock it out of the way and you could never really know. So we already went over the double slit. We went over quantum erasing, and now we're going to do quantum scattering, because this is the one that I thought was actually a reasonable way to be like, oh, okay, there's your actual proof, right? Because these experiments, double slit, quantum eraser, are all DS, man. Like they literally only see a diffraction pattern that corresponds with it being a wave always, and they're like, but particle though. So these aren't good, right? But this one gets a little dicey here. So, dude, remember when I had Joe Rogan call in? I had a note for it in the slides, Shane. So anyway, let's see, Joe Rogan, self-induced. Okay. So that guy, Arthur Compton, did an experiment here where he was measuring the wavelength of gamma ray emissions, and then they were converting that into energy. And then the expected amount of energy was supposed to be an amount that would be in alignment with the quote unquote classical prediction, right? And the classical prediction, obviously, they're tying their calculation to their atomic model, where they're saying that the photon is hitting a stationary electron, and the stationary electron is in the material of the deflector here that the beam of photons is going to hit, and then it's going to be reflected at an angle, right? And that angle is supposed to give a specific amount of energy output to it. and they measure, and they, what's that?
Ain't that like the energy supposed to increase with the wavelength, or it's supposed
Yes.
to increase proportionally?
Yep. Exactly. So with the classic effect, they're supposed to have a specific calculation, but this is again based on imposing specific conditions for the electron and how they're interpreting this, right? So they're saying if the electron has no momentum, no extra energy, and they have a photon hit it of a specific wavelength, so they have a specific energy amount that they know, and then it's going to hit this, and then because of that interaction, it's supposed to produce a wavelength that's proportional to that interaction, and they measured an amount that was slightly over that, right? So they were like, oh my God, what do we do? Classic mechanics is dead, right? Or your interpretation's wrong and you're just misapplying it. But, that could be one possible solution. But what they ended up doing was your boy Arthur Compton came along and he was like, hey, if we applied, hang on, let me see if I can find his math here. Compton, yeah, here we go. Okay, so if we apply, here's what Brian was talking about with it being proportional. I'll just kind of start over with a better slide of it. So we got the X-ray tube, we got the graphite. The electrons of the graphite are going to be stationary, right? For some reason, the X-ray is emitting radiation. That radiation is going to hit the electron. It's going to bounce off. It's going to produce a specific amount of energy that when it hits this, it's going to get reflected into an ionization chamber. And what that's going to do is that's just going to convert the energy into an electric signal that they'll use to measure like a pulse, like a frequency output, right? So they're like, okay, we should get this amount of electric signal based off of a conversion of all of that, right? Like the summation of all that is how much electricity are we going to get as a reading on our oscilloscope, essentially. So this is a graphic overview of what it would look like and what they're proposing. So the squiggly line here is supposed to be our photon. Now, obviously they conceptualize it as a tiny particle, but that would kind of get confusing in the diagram. So they represent it as a wave here. And then it hits our stationary electron with its zero momentum and all that. And then we have our scatter angles, right? And these are going to be based on the angle that this graphite target is tilted at, right? So when it gets tilted at specific angles, these energy scattering effects change, right? So for an angle that exceeds, I forget what it is off the top of my head, but I want to say that exceeds 160 degrees, they get, like, that's where they've quote unquote falsified the classic theory and only relativity can explain this, right? So how do they explain it with relativity theory? Well, Compton gives us this nice equation here. Delta lambda equals lambda prime minus lambda equals h over mc times 1 minus the cosine theta, right? So what are we doing here? What is this? Where did it come from? Right? But basically all they're doing here is, after a bunch of long-winded math that this very nice gentleman does on YouTube, he goes through like 3 chalkboards worth of math and erasing it and coming back to it. But what they've done here is that they use relativity, they use the time variable, right? So they take the XYZ coordinate system and they got the T in there for XYZT for relativity, because they added time as a coordinate in there. And because it's not an actual thing, they can store all kinds of stuff in there regarding like dot products and things and other abstractions that don't exist, that won't apply to the dimensions of an XYZ coordinate system. So they store it all in your boy T and then pull it out later on the back end. And they're like, look, this gives us the proper derivation for it. Relativity theory must be correct. This is the only way to explain it, blah, 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 et cetera, right? So what they're doing here is that and like the reason I was stressing the importance of the state of the electron and the graphite that the radiation is hitting is because if there's any additional energy, right, if you don't assume that it's stationary and it has its own energy, well, then none of this is necessary and the classic theory derives it all. Fine. Because it already does that for all the other angles, right? So then we get into this paper here from a guy named, Chu. I don't want to butcher his name, but it was like Chang Chu. And what he puts forward is that the experiment was originally done by Arthur Compton in a time when nobody had the experimental equipment to verify or, corroborate this. And the way that it works, right? This isn't an actual measurement of the. Can you hear me? Hello?
We hear you.
Okay. Fantastic.
Yeah,
so
I hear you now. Sorry if everybody else heard. I'm sorry.
Cool. So the way that that this works is So anyway, what they were saying is that Compton took these measurements, got the energy conversion, and because they're not actually measuring the wavelength, right? They're just measuring the energy conversion through ionizing it. That you can calibrate the instrument to kind of match what you need it to, and all subsequent observations and experiments are done, through this apparatus that basically give you this measurement, and they have to be calibrated and whatnot. So Chang puts forward, it's like, well, the correctness of this apparatus determines, like, the correctness of either theory is determined by what equation is used in this apparatus, right? Because you can use the classic theory if you just make a few different assumptions about the nature of the electron in that graphite. Or what was the other one? There was another one too. Oh yeah. So just by replacing the electron and introducing an electron field, this is something that Schrodinger did in 1928, where he put a 4-part lecture series on the electron field, and then you could explain all of this the same way by just removing that momentum interaction, blah blah blah. But anyway, the point is that it's not mutually exclusive to anything, but it's presented through this lens of only relativity, boys, only relativity. So yeah, you could use either equation, and it's not determined that way. A better way to do it would be to use an interferometer, so you could measure the wavelength and actually determine if if extra energy was created in that way. It'll have a wavelength to match, and you can measure that, and they never do. And then one company pretty much makes all the apparatuses that everyone uses. So people will be like, well, nowadays we did it in our physics lab, lab. Well, you do that by buying this apparatus from this company. Don't remember the name, but they manufacture everything and calibrate it to give you the result because you enter like what radiation you're using and all that. And it'll tell you, it gives you the outputs, right? So it's not so much of an experiment at this point. It's more of like they're just kind of going through the process of using this apparatus and reifying what's the output that's given to them by this equation. And then they're looking at it through that lens of a mutually exclusive interpretation of relativity theory, because they have a nice place to put all their abstract mathematics. And then this just gets into the detectors of the tubes. So this is just it's just the ionization process. It's just to further illustrate that there's no actual measurement of the extra wavelengths or anything like that. And this is just on the process of. What's that?
So this no way proves that photons are particles, right?
Not at all.
So this in no way proves photons are particles.
No, it doesn't prove they're particles. It doesn't reify the conceptual. Well, the way that they look at it, they say that it reifies, the atomic particles and subatomic interactions and all that. But there's no need for it. Like, you can interpret it differently and it's fine. So this is just the more detectors. And then a tiny universe made of cats, which I'm not going to redo that meme because I don't really even remember the joke, but it was, that's basically it. So this was their best proof, mutually exclusivity. You could only solve it through Compton's equation, where he used relativity to derive it, and all this stuff, and the fantastic story about it. But it turns out to be not mutually exclusive. You can, a different interpretation, you're good to go. Slightly different interaction of the electron, you're good to go. There was even a student where he was deriving. Yeah, I think it was this one where he was using the classical derivation for it too. And it was fine. It was like, guys, this is not even an issue, but it's cool to look back and reflect on the correctness of relativity theory. It was like one of those papers where they, they're like, it's not needed, but it all works out. So that's the Compton scattering, and that's what's supposed to further support the quantization of the photon to make it discrete packets of energy rather than a wave.
Wow.
Indeed.
I think the wave thing makes sense, like the pebble in the pond,
Are
and
you
the
sure?
wave spreads out.
You sure it couldn't be two simultaneous opposing things at once, sir?
Could be. All right. So if there's any,
I've been explaining that. Oh, sorry.
Oh, you guys gonna say if there's any more questions or anything like that, let me know.
No, I appreciate this, man. You break it down, bro, to make it understandable, man. And I know it, however some people see it, the way I see it, dude, I love it when you explain it, for each level of person, basically, for lack of better words. Just you break it down and break it down and break it down, the math and everything, and how it works, man. Is I've learned so much listening to your presentations, man. That's what I love.
I mean, I'm gonna have to run this back because I was lit at the beginning. But I mean, this us not getting neutrinos from stars thing is concerning. I don't know if I'm gonna be able to sleep tonight.
Dude, it's very upsetting and alarming.
What if found out neutrinos aren't real? No.
Yeah, it turns out some dude needed him to solve a math problem that wasn't even an issue. So what happened was they were measuring some gamma ray burst and they had a predicted amount for the energy frequency that it would emit. And then it emitted like a burst too fast or something. And they were like, oh my God, what do we do, boys? And they were like, oh, neutrino. this thing that's not charged, doesn't exist, has no mass, can't interact with anything.
I was just gonna say it'd be funny if that was the only massless chargeless particle they needed and invented out of nothing.
It's a free parameter.
Yep, dude, it's the freest of the free, bro. And then now they can't go back on it because they've experimentally verified it and all this stuff. So that's cool.
Why would you have real evidence? No, you can just invent new fake particles that will suit your needs for whatever situation you need them to prove in. You can always have the new fake particles corroborate the old fake particles. So
I was thinking with the gyroscopes and the interferometers and whatnot, they they act like they you've shown, and I've even been saying this for a while, about the linear interferometers, even using diodes. Like they say that the only thing that they act like the only thing they can measure is displacement, like rotational.
Yeah.
Period. But and to me, it's halted the freaking technology. Like just because you haven't put them on something fast enough at that rate to be able to detect it doesn't mean that they can't detect it. So Wayne found a way to do it, and to me, it's just holding back technology. Like we could literally have interferometers by now with the technology, measuring everything, measuring all movement, because they measure displacement down to like in the nanometers, right? So if they're capable of doing that, then to claim that all they could measure is rotational is absurd, man. It's just halting technology, man, in my opinion.
Yeah, I put up a screen share. So the other day, or it was yesterday, somebody was asking Shane how would you derive distances over the water without using the stars, right? Because we're just assuming the correctness of Haversines derived from the globe, which is derived from the, what's the word I'm looking for? The old graticule, right? So it's always going to give a distance that comports to globular theory, right? But it's like, how could we verify those and all that? Well, when you get into GPS and planes and whatnot, and the corrections for meridians and stuff, you realize that's not a reliable way to you can't use globe tools to falsify the globe in that way. But yeah, using a linear interferometer where you could measure your velocity with respect to absolute space, you could time how fast you're going and how to get how far you traveled to verify that stuff. And that's why there's a hindrance on it, and why these things aren't put forward, because the whole thing would collapse, right? Once you invoke absolute space for linear motion, people are going to be like, why can't we measure our Earth around the sun? And it's over. There's no more gravity. There's no more, none of that. Because everything is, there's no more big G applied to the solar system to explain anything, because all of that is contingent on producing a velocity of 30 kilometers a second.
Yeah. So it's almost like they got to find a way to, or an explanation, or really, no, maybe better said, some type of way to restrict that information from getting out while still using the technology. You know, they probably would have been had this, except it's taken a lot longer because they're having to wait.
Yeah.
Like you're saying, everything will collapse, bro. So they got to find a way around that before they can release that technology. That's my opinion, man. It might be a little crazy, but that's what I think.
Yeah. Well,
I mean, like,
go ahead.
Because they don't try very hard. Like, they don't even have to actually scoop it up. They just got to publish a paper that says, hey, when we looked at the background medium versus, the background star, sorry, not the background star versus this other star, it looks like the difference there looks like about 30 kilometers a second. We're going to scoop that up as, look, we found it. Right there it is. Look, Earth orbital velocity in the background stars.
Yeah. Well, they already tried to do that with stellar aberration, and that was falsified by Ares failure, or Ares success, I call it.
Yeah, that's better put. Ares success. And they try and go right back to the ether. Like, bro, they think the ether solves that problem. Like, you've still got the problem. I don't care what you're calling the light. It whatever you want to call it, the ether does not solve the problem that experiment or test, whatever people want to call it, that the results is not solved by abolishing the ether or anything like that.
So falsified, I don't mean the measurement, by the way. I mean the causal mechanism of the measurement. Because, like, I don't know if the measurement exists or not. I've never done it, but they have a lot of stories about it. But they assume that the causal mechanism of the measurement itself was that Earth is going around the sun at 30 kilometers a second. Because when you ratio the angle that they measured, which was 20 arc seconds, over the speed of light, they get 30 kilometers a second. So they were like, oh, Earth go rotate, boys, we're in. And then that's why Ares was like, okay, well, that doesn't actually tell us if we're moving or if the sky's moving, unless I put water in the telescope, introduce or, manipulated the independent variable, right? And that was the determining factor, because if the starlight was coming in at an angle as a result of Earth's motion, then when the starlight hit the water in the telescope, you would have to further tilt the telescope to compensate for Earth's velocity. And what they found was that they only had to correct it for a fraction of an arc second, 0.08 arc seconds, so not even a full arc. And they predicted that they would have to correct it by 15 arc seconds over the course of 6 months, and then they would have to bring it back by 15 arc seconds 6 months later. So for a total of 30 arc seconds, 1 kilometer a second per arc, right? So 30 kilometers a second. So this was what they were trying to do. Now, when they took the measurement, they only had to move it a little bit. The implication is that the Earth is stationary and the starlight already comes in at an angle. And if it already comes in at an angle, that means everything in the sky is apparent and there's no proper location for anything up there. And
right, man.
So
listen, whether it be particles or whether it be waves through the ether, it's still supposedly in their model. It's in taking that path. That's why I was saying the ether, of trying to get rid of that, is in no way any solution to that problem. Because, like, if you're going to measure something moving and you're going to look at it through a lens or a camera or whatever, then yeah, you could tell. If you slow the light down, you could tell what's moving. I mean, I've personally never done it, but I mean, it just only makes sense. You could tell which one's moving by the corrections you have to make.
Yep.
And
exactly.
It doesn't matter if there's ether or not, whether it's particles or waves. It's still taking that path. So you should have to correct for that, period.
And it gets even worse too, because my favorite paper here, Mickelson Morley, like, what do we do? How do we Ares failure out of this? Why isn't there more documentation on it? How do we know? Is it just some stuff flat earthers made up? Well, let's see what Mickelson has to say in 1887 regarding his experiment on relative motion of the Earth in the luminiferous ETH. So he goes on to talk about the previous experiments that were done to measure Earth's velocity through space, and he says, but it failed to account for the fact proved by the experiment that aberration was unchanged when the observations were made with a telescope filled with water. For if the tangent of the angle of the aberration is the ratio to the velocity of the Earth to the velocity of light, then, since the latter velocity in the water should be 3/4 its velocity in a vacuum, the aberration observed with the water telescope should be 4/3 its true value. And then he goes on to say here, and I'm screen sharing if you guys are able to see it. So then he goes on to say, he puts a little cliff note here. He says, it may be noticed that most writers admit the sufficiency of the explanation according to the emission theory of light. And the emission theory, I think, yeah, that was the ballistic light theory. So they thought that light was like little little particles, right? And that was falsified by Arago in the 1800s when he did the Arago spot experiment. So if you take a coherent beam of light that hits a sphere, the light will, diffract around the sphere and recombine, and then put a center dot directly behind the center of the sphere, as if the light went directly through the sphere. That's obviously not what happened. It diffracted around and recombined, and that was the postulate hypothesized, or the postulate of the wave theory. So everyone was like, okay, so emission theory is full DS. So anyway, but this is back when they were still kind of, could be either or. So the difficulty here is that for the emission theory, the velocity has to be greater in the telescope, in the water-filled telescope, and therefore the angle of aberration would be less. So what he's saying here is, if you think light is a little particle, it has to enter, when it enters this water-filled telescope, it has to somehow accelerate by 30 kilometers a second, so that it doesn't have to be corrected to keep it in the center, right? And then he goes on to say,
not slow down, right?
Exactly. And then that would violate the conservation of momentum, because that's not how that works at all for them. So like they don't accept that. That's an absurd hypothesis to explain it. And then he says, hence, in order to reduce it to its true value, we would have to make the absurd hypothesis that the motion of the water in the telescope carries the light in the opposite direction. So here he's talking about the difficulty for the undulatory theory. Sorry, I missed that part before I continued on. So he says, while the fact of the difficulty is even greater according to the undulatory theory, so that the undulatory theory would be the light being a wave. So if you think light's a wave, then when it hits this telescope filled with water, it has to be carried in the opposite. There has to be ether in the telescope that's carrying it in the opposite direction of motion, right? Which is super untenable, right? Because this was hypothesis makes it worse. It still doesn't help. And the issue with that is this was derived off of a stationary ether theory. So they were trying to attribute any correction angle to the velocity of the Earth to make it, mutually exclusive. And then, so to say that the ether is stationary, but for some reason in the telescope, it's bouncing around, carrying it in the opposite direction, such that you won't have to make a correction, is obviously, not good. And that's what Michelson was saying here, that it's absurd. And that's what they would have to put forward. And then he goes on to close here at the end of the paper by saying that the measurements that they made of 5 kilometers to 6 kilometers a second, which don't correspond to 30 kilometers a second, cannot be explainable by Stokes or Fresnel's explanation for aberration, which is a stationary ether theory. And then he goes on to say that Lorentz's theory can't explain it either. Now, Lorentz had a stationary ether theory with link contraction and time dilation, where a rigid body, which, removes the meaningfulness of the word rigid, but anyway, a rigid body moving through space will contract proportional to its velocity, right? It'll contract in the direction of its of motion, proportional to its velocity. And they can't use that either, because the measurement was 5 kilometers a second. So, and not like 0. Like if it was 0, they could Lorentz contract, time dilate, because that's what they ended up doing with special relativity. And these are the same mathematical frameworks, just one has an ether that's doing the compressing as the mechanism, and then the other just has a space-time distortion, and your molecular structure compresses. There's actually no physical mechanism proposed for link contraction and time dilation. It's supposed to be some sort of an apparent effect relative to your velocity, and it would be measured differently to observers at different velocities. So anyway, there's no actual solution here with a stationary ether theory, is what he's getting at. So yeah, that's just to end on that.
To end real quick, there are literally people who say, like, this ain't an experiment, and this ain't an experiment. Flat earthers.
Oh,
say,
dude.
these are easily experiments, man. The phenomenon is the motion of the stars and shit. And
No.
the
Well,
hypothesis is that we're in motion or the stars are in motion, and so you could vary it by moving the telescope or slowing down the light. I mean, this is obviously experiments, man. It's crazy people say that they're
dude,
not even experiments.
crazy that they say that. You actually were super correct there. Let me further back you up there on how these are experiments. So I did a presentation titled "On the Orders of Measurement and Experiment." Now I'm not going to do the full presentation here because it's at least a 2-hour. But when we get to Michelson-Morley, or I think they have an MMX. Nope. When we get to Michelson-Morley here, is this an experiment? Well, the control would be the known wavelength of light. And how did they know the wavelengths? Well, they had been measuring it since the 1800s with diffraction grates and prisms, splitting the wavelengths, measuring them manually and all that. So they were well aware of how they could, of what was being emitted from the light source, right? And then now they were going to utilize that in experiment. So as Brian was saying, your hypothesis is that the Earth is in motion around the in motion around the sun. And what you could do to substantiate that with an experiment is you could set up an interferometer where you would have the known wavelengths, you would have the predicted value for how much the beams would recombine if there's no velocity measured, right? And if there is a velocity, you can derive using this equation, which is the equation that they use, same equation that they use for inertial navigation systems to derive the Sagnac effect, and what was shown in 2001 by Ruyang Wang to be generalized, right? So they were spot on with with their interpretation of light and the relationship with how to measure relative velocity using light, because it's literally the same equation. So they nailed it. So they had their prediction for how much light would be displaced at different times a day when the Earth is aligned, parallel, and perpendicular to the direction of motion as we're going around the sun, right? So the variables there, the IVs and the DVs are going to be your time of day and the orientation of the apparatus, right? So as you're rotating it and changing it with respect to the time of day that you're taking the measurement to see if you're going to get those min maximum fringes that we talked about, that's literally an experiment. That's like the time of, you might not agree with it or the premise of why they're doing it, but if the Earth was moving, like this is how you would do that. You would take measurements at different times of day with a device that would rotate to be aligned parallel and perpendicular to the assumed planes of motion where you would get your minimum and maximum fringes. So
and you could collaborate that with measuring anything else.
Exactly.
Even if you wanted to go as far as saying diffraction is natural observed phenomenon, that if that's what we're measuring, is the diffraction. In a sense, that's kind of what's happening. I mean,
well, we're measuring a phase difference. So
you could.
Yeah, well, it's measuring a phase difference. So it's actually, when we were talking about the induction rates earlier, the induction rate going with motion is faster and the induction rate going against it is slower, right? So it's actually even a little more than just a diffraction pattern. It's the literal induction rate is physically changing purport to be reflected in a measurement.
So I'll close by saying that it's just as than an experiment than the freaking double slit or constant scattering. Just as much if not.
Oh, dude. So
all experiment.
No, so you can 100% stand on the quantum eraser experiment being an experiment because the IVs in there is the configuration of the apparatus, like where you're putting the slit in. Is it going to block or go here or go there? The whole using your consciousness as an explanation, that's just mysticism that's put forward to explain it, right? That was shown that it's always the same diffraction pattern of a wave. You just recombine the pattern and that's it. It's just literally just put out there to confuse people, to make them think that light is behaving in a way that it's not behaving, so that they can continue to use this abstract mathematics to reify a system that doesn't work so that they can hide ether.
Yeah, it all stems from breaking the globe. Strangely enough, it stems from them trying to keep the Earth in motion and their atomistic, materialistic worldview, them refusing to even consider anything else.
Yep. Yeah, it's literally just designed to get you to stop from thinking about that. But yeah, you're absolutely right, dude. Time of day, and with respect to the orientation of the device. And then you could break it down even further, right? So you could take the closed loop and you could just do times a day. So you could say like, is it just the orientation? Is it just this? Is it just that? You could further refine it and precisely figure it out. And then you could introduce additional variables. And that's what Miller's work was all about too, right? So he was really refining this orthogonal setup, right? They call this the classic Michelson-Morley setup where the light ray goes orthogonal to itself. So he really refined this by using different wavelengths, he would introduce different ways to heat up the apparatus, ambient heat, direct heat, different times of day, different locations, elevation, doing it in a vacuum, just adding wood coverings over this changes the readings a little bit. How crazy is that?
To break it all down, interferometers are not parlor tricks.
No. Dude, dude, check this out, bro. This is the baseline of interferometry, right? This is what it started. This is sunlight, a crystal mirror, a crystal that's been polished, right? So that it's you can see through half of it, right? And then mirrors to reflect, and then water, right? If this isn't an experiment with like naturally occurring phenomenon and devices and stuff, then nothing is. Then there's nothing that's objectively an experiment, right? Because this is the most natural you could get, dog. Literal sunlight, mirrors, and crystals and water, and then you just measure the pattern that's produced when the beam recombines.
Yep. So
And they just built on that, right? They just built on that. And now, what they won't do for Earth rotation experiments, right? You know how I was talking about earlier. Well, how do we manipulate that IV? Well, if you start doing these at elevation, they're not going to give you 15 degrees per hour, boys. That's what Miller's work, Galileo's, all that was about. And Picard. So there was a couple of balloon experiments where they took balloons up, hot air balloons up to about the same elevation that Mount Wilson was at. So about 2,000 feet above sea level. It's like 19 something, but I forget off the top of my head. But anyway, and they took different what's the word I'm looking for? Interferometers with different configurations such that like the arms are different lengths, and those produced different measurements. But the one time that they took the apparatus up with where it was symmetrical, right? It gave agreement with Miller's work. And then they use the other experiments where the arms aren't the same length. And they're like, look, it's not doing the thing correctly. And it's like, well, yeah, that's not how it's, you're like, yeah, it's like, well, that's not how it's done. Right. Because you can look at inertial navigation systems now and it's symmetrical, right? Like if when your arms is longer, it's not going to produce the desired result. So anyway, that's just like some little additional gravy on that. Regarding, is this an experiment or not? Absolutely, man. Absolutely.
One last thing to put icing on the cake, like you could put me in a giant box and I could use science and give me an interferometer and I could make an experiment, see if something was rotating, like if either I was spinning in a circle, like spin me in a half circle real slow, or if let's say the pylon in the distance, this small little pylon is moving in a circle. I could use an interferometer to figure out whether I'm the one that's moving, or I don't have to move the whole. You know what I'm saying? That's what I've heard people say. I don't have to manipulate and move the entire Earth to prove that I'm the one in motion. And so yeah, it's definitely an experiment. That's all I had to say.
No, it's super important, man. Because like I've heard a lot of back and forth where it's like, is it an experiment? Is it not? Like, is it a demonstration? Is it something that changes with my consciousness? And like, no, man. No, these are all experiments, right? You just got to know what's actually being measured and what the purpose of it was. And then you can go from like, you just like, oh, okay. So these are this is your control, IV, DV, all that, right? Time of day, manipulating the time of day you're taking the measurement.
Which is most definitely, I used to fight that way until I really just took a breath and looked at so many examples where it is absolutely independent. And it absolutely does show obvious change. It's like, dude, I'm just ignoring that. For some reason, I'm being blockheaded. I had to open up my mind and really just look at the facts. And so it's definitely part of a cause. Maybe it ain't the full cause, but there's nothing in nature that is just one single cause and that's it. There's always multiple factors, and time can definitely be independently varied in experiments. Especially chemistry and stuff, man.
Yep. Oh yeah. So here's Galev's periodicity. So we're looking at the graph here where he's plotting the A and B. You know how I said earlier he had an upstream and a downstream for his radio link. So these are those two plotted against each other, and then over top. So it's symmetrical and exactly what Miller measured 30 years before him. And this is a topographical. This is a side view of what it looked like. So he's up here at an elevation. You can't see the other one second. So you see he's up here at an elevation A. He's sends his signal out, hits a reflector at D. So he can see how fast the signal gets sent to B versus how long it takes if it hits this deflector and propagates at this altitude versus if it propagates from C at this altitude. And from taking the differentials from that, he established that vertical gradient that Shane linked earlier. I think I have it on a slide here. Nope, that'd be too easy. But yeah, so anyway, his measurement matching Miller's work, super pivotal to the ether stuff. Yeah, that's it, man. That's it. So does anyone else have any questions or comments or anything like that, boys? Oh, okay. Well, if no one's got anything, we can do the quantum flaw real quick, right? So earlier I was talking about E equals HV and how there's no time variable in it. Oh, 1 second. There we go. I was talking about E equals HV and how there's no time variable, but how sometimes it makes the correct prediction, et cetera, right? So they use this to reify vacuum propagation, right? Because there's no medium for space, right? It's an empty medium, but light propagates through it. So how does that work? Well, light's actually quantized little discrete packets, right? From E equals HV. So what was pointed out in 1995 by, can't remember her name, but what was pointed out by her in her paper was that if you take the momentum of the light, right, because it has to have some sort of momentum to get through the vacuum to be physical, even though it can't have momentum, because if it had momentum in the classical sense, it would have mass. And if it had mass and if it was traveling at the speed of light, it would be a huge contradiction and break everything. Nothing would make sense. So how do we give light mass without any of that, right? So that's where this E equals HV comes into play. And they're relating this to be the momentum of the photon, right? So if you take a photon that's 3 gigahertz and that exists for 1 second, right, its oscillation rate would be 300 times a second. So it would be, if it was a physical entity, if this discrete packet of energy, if this Planck's constant was a discrete packet that was proportional to the frequency, it would be 300 million meters long. So it would essentially be any photon, and then you could expand that to any wavelength or any frequency amount. Where it's just going to be proportional to the length of its existence, right? So they say that the stars are, 5 trillion light years away, but we're getting these E equals HV packet propagations through a vacuum. Well, guess what, my dude? You just got hit with a 5 million light year long photon, right? Now you can introduce a time variable in here and fix all this, and it's not the biggest deal. But there's also instances where it breaks the wrong prediction, where suppose you have a laser of a certain wavelength that's supposed to be a red wavelength, and you apply this equation to its energy over the course of 1 second, and you're like, cool, if I turn this laser on for 1 second, I'm going to see a red wavelength. But if you flick it on and flick it off real fast, sub 1 second, it's not going to have enough time to exist at a wavelength that's going to produce the red wavelength. And it would be like green, for example, right? It would be outside of its red wavelength. It would change, because it's at a lower oscillation rate. So you're not going to see that red color. So it makes the wrong prediction in that regard. It's not a physically binding equation or anything like meaningful. It's a cool proportional ratio that goes with that 1 second experimentally value from 1901. So it's cool. It's cool when it lines up occasionally, but is it physically meaningful? Do things propagate through a vacuum? No, because if they did, they'd be proportional to the length of their existence.
I think maybe you're missing some free parameter that's out there. So
yeah. Absolutely. Cool. All right. Well, I've run out of quantum things to debunk.
Good job, man.
So
that was intense. That was a lot. There's
yeah.
a lot of stuff in that.
Yeah, it's a lot, but it's pretty straightforward, right? There was an ether, a fluid medium that permeated all of space, and all of motion would be relative to that. And when they tried to measure the motion of the Earth against that medium, they kept getting results that didn't meet the predictions that would confirm the Copernican principle, right? That the Earth is in motion, right? That the dynamics, that the Newtonian dynamics that they applied to the sky that are supposed to back up Kepler's laws, right, which are just purely kinematics, right? It removes that explanation, because if Newtonian mechanics were true, then then the Earth is moving at 30 kilometers a second, and you'd be able to measure that for sure, especially against a fluid medium and all that. So that's why they have to get rid of that. And then by doing that, they were forced to turn the ether into separate fields, an electric field and a electric magnetic field for the photons, right? And then there's an interaction with these fields, and that's how they explain everything. And they get into problems right off the bat by just starting with an uncharged particle interacting with the field. They're already bankrupt right off the rip, dog.
Hey, let me ask you a question, Alan.
What's
How
up?
much of this information is just freely available? Like, I know some of it you probably had to find people who found links, and I know you found most of it probably. But I mean, how much of it is actually just readily available? Any of it?
Yeah, I mean, you find it on the internet, right? Like, you just keep researching the stuff. Like, I found it all through, a lot of this stuff was on Google Scholar, but I'll say this, when it came to Compton scattering, and I was trying to find different explanations for this was one of the hardest ones. There wasn't a lot on that until my boy Chang showed up and set me straight and really broke down what we were looking at here and the assumptions that are baked in. And I was like, oh, thanks, Chang. And then there was the other guy who derived everything with classical mechanics, but then was like, but relativity is super correct, so it's all good. But yeah, it's all like available. I guess you just have to, read it and then go against the grain with it, right?
Understand it, yeah. Break it down. So all the information's there for everybody. Just
break
it down.
Like a lot of information that came from this presentation here, the quantum part 2, a lot of it was covered from that paper from Oliver Kanza, and he just breaks it down like through the narrative of like, this is the time, this is the state of physics, and they had an experimental value, they did their measurement and it was wrong, and then this is the first attempt to rectify it, second attempt, third attempt, right? He just breaks down each one of them in a pretty straightforward manner. It's a pretty easy read. It's not overly complicated with math. It's just and all the math in it that he's talking about he's already correct. He's not saying anything incorrect about it because it's already canonized in the story of quantum field theory, right? It's already part of acceptance, and you could read about these people talking about it in their biographies and stuff. So it's not like that dude just went on a limb and was like, he never derived it. It's like, buddy, they held a conference to try and figure out how this guy derived anything, and nobody could ever do it. And nobody could ever solve it in a meaningful way, et cetera, right? So
that's crazy, dude. Hey,
yeah.
What was that guy's name who tried to dispute all of Miller's, enormity of work, like Shackleton or Hackenberg?
Yeah, so that was Shankland, Robert Shankland.
Yeah, Shanklin, dude. Like, bro, they just look at Shanklin and act like everything. Just point out Shanklin. Crazy, man.
Yeah, Shanklin, and that wasn't even the good one because that one was pretty weak. The data sets that he referenced, one of them was from Millard's controlled experiments where he was purposely trying to make the fringes zero, and like manipulate them on purpose. So like they took it from that and they were like, look, see, there's no fringe here. And then I forget the other stuff they did. It's been a while since I've done the Shanklin gauntlet. What's the other thing he did? I can't even remember, but yeah, then there was the Thomas guy, which is the more preferable one, like the higher end debunk of Miller's work, right? That they say, but Toby took a big dump all over that. So yeah, there's really, and then the fact that it was measured again, like it's because it's not just like, okay, well, we have Miller's measurements. We don't have, we just have these stories about how they're debunked. And it's like, well, we also have corroboration of it in, Hector Monera in 2002 and 2004 used a Michelson interferometer he left it running for 3 years straight and measured the same periodicity that Miller measured. We got Galev doing it with optical wave bands and radio interferometry on the millimeter spectrum. So the most precise, wavelengths you can use to make the measurements, they're just constantly verifying Miller's work. And then to the point where it's even like there was some experiment that they did in 2019 with a resonance cavity where they were trying to verify the one-way speed of light. And the corrections and stuff that they applied to it, right? They literally applied variations for what do they call it? Sidereal. What do they call it? Daily seasonal fluctuations or something like that. And it was like, what? You mean variations relative to the equinoxes? You're talking about you're correcting for Miller's variances that he measured, and then you're gonna turn around and say that the one-way speed. That's like, all right, man. Like, all right, dude, you guys are on crack.
Whatever it takes, man. Whatever it takes to maintain what the shit that there's the shaky foundation that they already have. To me, with the Michelson Morley, it's like saying, we're in a current in a let's say in a river or something, and we're rotating around this island that's in the we know for a fact we are, but really in reality we don't know whether that we're in a current. Like they went to measure this motion and it wasn't there with the interferometer. So it's like they just abolished the water. Like they literally, to me, that's basically what they did. They didn't get what they predicted, so they just abolished the damn water itself. That's kind of what I feel like Michelson Morley did with the ether.
I mean, that's essentially what happened. Right? There's no other way to look at it, really. Oh, what was her paper called? Catastrophe. Yes, found it. So my boy Eric's asking for the paper here. I'll put it in the live text chat for the quantum flaw for anyone that wants to listen to that or learn more about that. So yeah, and then what's that lady's name? Not Physics Girl. What's the other girl? Fractal Woman. Fractal Woman has an excellent breakdown of the quantum flaw, and she fixes it with introducing the time variable. So let's see, quantum flaw. Let's see if I can find it here. Oh, she has a Compton scattering video. I have to watch that.
I heard there was a lad gave a quantum presentation.
Yeah, bro, you just missed it. I just did 3 hours on it.
Dang, man.
We're just doing Q&A and just kind of talking about other related stuff. Oh, here we go. So this.
I was doing engineering stuff for like 4 hours.
This. And then, nice, you engineer some cool stuff.
Not really.
Nice. So yeah, she has an awesome breakdown of the situation. And then she even fixes it so you can't even be like, oh, it's a full debunk. Like, yeah, you could make it work if you just introduce that. But the fact that they don't address it kind of reveals it's not physically meaningful. So anyway.
So what are neutrinos?
Oh, nothing. From nothing comes nothing.
Oh, did you get a different mic?
No, I turned off noise suppression. Does it sound better or worse?
Your voice sounds softer.
You sound softer. Don't you try and sweet talk me here in front of the boys?
I think your voice is like half an octave higher, no cap.
Yeah, well, let me turn it back on. How does it sound, meow?
The same.
Cool. I have no idea then. Couldn't tell you. So anyway, we touched a little bit on interpretations of reality and how the quantum field theory is not mathematically coherent enough to give a physical explanation to anything, and how we should probably go back to the old vortex theory. And you're the resident vortex theory J.J. Thomson expert. So if you would like to talk about that or give a little rendition on that, and the significance there, right? Because it's just replacing a story about what you think's happening, right? It's not, doesn't mean it's real, right? But it is more coherent and uses least principles, right? So when you get into the atomic theory and all that, you can't even derive it kinematically because you have to assume the strong and weak nuclear force to stop anything from ripping itself apart or collapsing it on itself. So it's already not looking great. But anyway, if you want to talk about the vortex stuff, bro, that'd be sick.
Well, in the standard atomic model, they have to introduce forces which in and of themselves require an explanation. These intermolecular forces, right? And they just posit all these 4 fundamental forces as fundamental. They don't introduce like a mechanism of action. They just say that they just are fundamental, right? But if you look at, what you just said about QFT, when their experiments didn't match predictions, they just assigned new coefficients and named them virtual particles to account for the error that they had. Not that virtual particles actually are anything, that as if they're actual independent entities. More, it's just a naming convention used to describe how much they were off by. So then you say, well, what's physically happening? Well, that's what J.J. Thomson was trying to do. He basically proposed a theory of matter in which he hypothesized that all matter was made up of tiny toroidal vortices, which he called vortex rings, within a universal fluid, and that these rings could link together and form bigger structures, which would in turn end up forming molecules. And the size and energy and motion, magnitude of motion of these vortexes are all linked together, such that basically the more energy within the vortex, the larger it would grow. It would accrue more entrained fluid in motion, so to speak. So if you take that, right, because this was in 1882 that JJ made this idea, you fast forward 140 years in the future to today and look at it through the lens of some of the things that we now know. They didn't even know about mass energy equivalence back then, the way that they would use energy to measure quote unquote mass. But if you believe that's a thing, because 99% of the way we can use it for most intents and purposes pretty accurately, then if you want to say why is it a thing, going back to the QFT problem, what's the physical explanation behind it? You can't just say that mass and energy are equivalent, that they can just be exchanged back and forth readily anytime you want. Like, what's physically happening? Well, I think if everything's explained by vortex model, you get the ether, it's the fluid. If the ether's in motion, then that motion within the ether is definitionally energy. The more motion you have, the more energy you have. The more energy you have, all the energy is that motion in the ether. It's ether that has been whirled into this velocity, which has caused it to take on a vortexual shape, which holds its form. And then as these vortexes grow and link together, they form new elements. So they go all the way up the periodic table. Yeah, that's what creates mass. The more motion you have, the more ether you have swirling, and the more ether you have swirling, the bigger the vortex gets. The bigger vortex with the more ether in it, it's the more massive. That's where we get weight.
So we wouldn't even need the 99 empty space with that explanation. That sounds like a solution for a lot of just obstacles that they seem to run into. It makes sense on its face just listening to it. That's interesting as fuck, dude. Excuse my language.
Dude, yeah, it's way more coherent to have a fluid medium that's, everything is interconnected from, right? Because here's the thing with all this quantum stuff, right? We didn't really get into all the ridiculous names of the different flavors of quarks and leptons and gluons and all that, and the anti-particle pair names and all this stuff like that. But the important part to note is that it's just an energy fluctuation that can be represented by a myriad of models, right? We're just in this paradigm where they've got us locked in with these fantastic stories about a theory that has no physical meaning and isn't mathematically coherent. So,
yeah, I think all the crazy lepton quark stuff, all those different particles that they've made all these names for, and flavors and stuff, are most likely intermediary states or leftover sums of energy from the processes that cause the vortexes to link and unlink and split.
Oh, thank you. That was the bigger point I was trying to make. When you get into all these different derivations, right? They all come from the same thing. They all come from the same source, right? They're all fundamental. What they're implying, right, is that there's a primary substrate that all these are the source that is the source of what's being measured, right? What they're conceptualizing as an electron versus a muon, right? It's like, well, where does it come from? Is it a different particle? So there's an uncharged particle, but does this uncharged particle have a different weight than the uncharged electron particle? Because this is when it you know what I mean? There's none of that. It's all goes back to the same thing. So it doesn't matter which flavor of quantum theory you believe in. You're just accepting more or less a more or less amount of fundamental particles to explain pressure mediation, high to low, which is easily explainable with a vortex and hydrodynamics, right? So, you could streamline the whole thing and make it coherent instead of having different flavors to, do pressure mediation for you, where you've put a force where there couldn't be one because it wouldn't, mathematically work. It would rip itself apart, etc. Right. So just like that's the significance of it, right? It's not that the vortex theory is any more truer. It's that it makes sense and you can derive it under similar principles that are relatable to reality, right? Like hydrodynamics is a real thing. You could measure turbulent laminar flow relative to different Fermi surfaces in insulators, right? So, these are real things that are applicable, and I like interpreting it through that instead of going, okay, here's what we're gonna do, boys. We're gonna store all our abstractions in another abstraction, and then we're going to come out the other end and say this is mutually exclusive and everything's disconnected forever.
Math magic.
It gets more obvious too. The contradictions stem from within themselves.
Yeah, I definitely wasn't expecting to come in here and comment on that, but I would have, been prepared to say more.
Oh, dude, you're straight. It was a great explanation, nice and slow, and it gets better every time I hear it. So,
thanks, bro. Yeah,
yeah.
The geometry is honestly one of the most interesting things. I was studying a little bit yesterday, kind of sidebar to that about how insulators or dielectrics rather are able to store charge. Okay, as you might know, conductors are not the storehouses of electrical charge. It's actually dielectrics. Just like in a capacitor, you have the two plates on the top and bottom, but the dielectric in the middle is where the charge is actually stored. Same thing with a Leyden jar. And when you think about the model of current particle physics and the way they teach electricity, they teach that current, like, or electricity, right, energy, they teach that it comes from the flow of electrons. But then when you look up, like, well, where is the charge being stored in an insulator, they don't teach that there's a bunch of extra electrons that flow into it. What they teach is that it creates this basically dipole alignment between the dipoles of all the molecules inside of it. The electrical current that's being applied to the dielectric causes a realignment of the poles, and so it causes the charges that are already in it, the protons, electrons, just the normal molecular charges, to actually space apart further than normal. And so it requires a certain amount of energy to pull those bonds, those charges apart from each other, because they want to attract, they want to stay close. So whatever amount of energy it takes to hold them apart, that's the amount of energy that's being stored. And what basically happens, the way they explain it, is that when you put enough energy into it and you get them far enough apart, what will end up happening is, because there's this, I mean, it's just like a giant honeycomb network, right, of like a bunch of different shapes in every different direction, is it'll end up getting into such a configuration that the geometry the new geometry it's put under ends up finding stability in a different position than it was before. And so it'll get stuck like that. And so the energy, in order to go back to its original state, it'll have what's called an energy barrier. It will take more energy to, like, move out of the current geometrical configuration back to default than it does to just sit there at rest. And so they've actually used this concept to build a lot of tech. But if you're not able to get it above a certain temp, it'll hold on to its charge, and this is how they're able to keep dielectrics, like, holding on to current. This is how they explain it. But the thing is that the part that doesn't make sense, because all the geometry stuff makes sense, right? The thing that doesn't make sense in their model is that when you actually ask, where is the energy itself being stored, because we get it, like what the energy is. The energy is the force required to hold the bonds apart. But where is that energy being kept? Where is it being held? They claim that it's being held and kept and stored as potential energy within the electric field itself, as if the field is its own entity, separate from the molecules themselves, and it exists, within free space, and it can perform work via action at a distance with no mutual contact. You could take a vacuum chamber, right? Separate it, like with walls all around it, thick walls, and you could have an object on one side and an object on the other side, and that object on the one side, you could crank up the charge on it and have it create an electric field. That electric field could reach all the way through the vacuum chamber, all the way to the other side, and interact with the object on side number 2. And they claim that the field in itself is nothing substantive, but their definition of the field is a conceptual construct. So it doesn't.
That's crazy, dude. That's crazy. So in other words, the more surface area, the more of its own field it can create to store itself. That's crazy, dude.
It's not even a surface area. The problem, right? It's the same problem as QFT. They remove the ability to have a meaningful physical explanation for the phenomenon. You can measure it all day. No one's contesting the measurements performed, but how is it physically meaningful if it doesn't serve as a substantive explanation for anything, right? You can't tell me that a field is just a numerical construct that we use to quantify like the potential to do work and energy and stuff. Like, okay, so you're saying a field is just a number device that you've made up in your mind in order to be able to quantify stuff. Cool. But it's actually holding on to real physical energy and performing real physical work across free space. So what is it? Like where is the energy? You can't create a circular reasoning definition for a field to explain what it is and where the energy is at. But if you have a fluid, if you have the ether, if you have a universal fluid, if you have a primary substrate that provides a physical substantive mechanism by which the energy can be stored in the field. Because the ether is ever present even within the vacuum.
So the field doesn't just follow the electrons around, waiting to it's just I don't even know the word for it.
That's the thing. There's nothing there. Like the field isn't a thing that you can touch or see. You can feel the energy, but you can't actually okay. The electron, right? I know you can't actually see an electron either, but let's pretend that you could, because on their model is just too small. But let's pretend that you could zoom in enough. You could see electrons flowing along a path. If you could zoom in close enough in their model, you could definitely see the electrons, and they would be flowing. Okay, cool. Well, that means that the energy, this current, is actually physically made up of real physical electrons that are existing physically in space that I can see and touch. Awesome. What's the electric field, though? There's not a thing that I can look and see and touch and feel. It's not physically substantively there. There's just emptiness. Even within the vacuum, in the emptiness, the energy of that field can reach out and touch me. This is why in QFT they invented the quantum vacuum. They basically redefined the vacuum and redefined fields in order to make fields fundamental entities from which the entire universe subsists.
Well said. Yeah.
They kind of talk out of both sides of their mouths.
And then, you know what's crazy too is when you go to question them on it too, they'll go, it's fundamental. You can't question it. It's like, what? What do you mean? It's like, it's off limits. I can't, hold on. I can't question the fundamentals of the backbone of your model, of your belief system. I can't question it because it's fun, because it's assumed to be correct or exist or whatever. Like, no, that doesn't, it's not how it works at all. You obviously question the fundamentals.
Very nice talking.
Hey, Laura.
Something about vortexes or something.
Are you talking through like a voice changer or something?
I'm just not very good with technology.
Yeah, I agree, Alan. They're like, fundamental would mean that it's the smallest, most basic, most, you know, uh, low level intrinsic thing that there is. You can't get any more basic or primary than that.
I can't pull over any further. Whatever, right?
Yeah. But then when you cop out like that though, you don't really do a very good job of explaining what it is. It's just a fundamental thing, okay, but like what is it? Like can you describe it more for me? Like its composition, its substance, that they can't do any of that.
Dude.
No, because some things are not meant for those who do not grasp the truth of reality. Everything is about money. Money is power, it's energy. It's what you need to live, yet it's not required for anything.
Yep. So to quickly recap, quantum superposition, quantum entanglement, the which way experiment hypothesis, thought experiment isn't real. It always shows the diffraction pattern that corresponds to light being a wave, always. And what do waves propagate through? What's being inducted? Where is that energy being stored that Pizio was just talking about? Where do you put it, as Stone likes to say? It's in the ether. Oh no, but if I look at this experiment while it's going on, my consciousness, yeah, dude, cool. So did you say you had a measurement of the particle pattern or no? Still no? Okay, cool.
It's crazy to me that they don't actually have like any actual, Dr. Quantum double slit photon particle beam measurements, because I've heard my whole life that they do. You know what I mean?
Yeah, dude, they don't even have a single photon detector. That's a scam too. Your boy It's BS has a video on it. I forget the specifics off the top of my head, but it's insane. It's like they don't even have a detection rate that would correspond to being fast enough to measure a single photon, like the rating limit or whatever.
Because they would have to break it down to like the
dude,
whatever frequency corresponds to the speed of light on like a hertz setting.
Right. It's ridiculous. It's a literal scam, and yet so when you read these papers and when you hear these people talk about it, and they're like, "There's a single photon." Guys, there's never, ever once been a single photon. Never. It only exists as a math tool when you E times h nu, which is Planck's constant. Planck's constant times frequency, right? So it's the only time you're gonna see that. Oh, but the momentum, the measurement, it is yeah, dude. So that momentum, that intersection point that we were looking at earlier when I was saying that Maxwell's displacement current gives them the freedom to say, oh yeah, when the electric field as it's accelerating will self-induce the magnetic field. No worries, lads. Yeah, that is the ether. That's the thing that's doing what's being measured. That is the phenomenon, right? So everything is in relation to that.
They claim that the electric and magnetic fields can self-induce each other like ad nauseum forever.
Yeah, dude, literally, dude, we watched that MIT video where that student was like, hey, how does that even work? And he was like, well, you see here, the electric and magnetic field are like little children, and they have parents, and they grew up in a house, and they were part of a family, and then they became of age, and then they left the house, and now they're doing their own thing. Dude, what? What was that? Did you just describe the plot of the Sims game? Dude, that's not a real thing. And then he goes on, and then he's like, yeah, we have some math. And then Walter Lewin's explanation was even worse. He was like, oh, dude, maybe there's electric scattering on it. What?
What does that even mean?
What? Oh, I'm sorry. That was for a different phenomenon. I apologize. That was for the free electron theory and where it's stored.
I think you were thinking about the
I was talking about radio propagation for the other guy, where he was like, and then they grow up and have a family, talking about how the field self-induces.
Yeah.
So that was in relation to electromagnetic propagation. And then the other joke was about the free electron theory and where it's stored. Sorry, got those mixed up for a minute.
What's his face? Feynman tried to say that Leyden jars have charge on the dielectric surface because of electron spraying.
Yeah.
Because they overcome
Yeah, Walter Lewin said that. Yeah, Walter Lewin said that. And then using a bunch of assumptions that aren't relatable to the anything. He was like, look, I derived it in this scenario where it only applies here. It's like, sick, dude. Great job. But I prefer the story about the electrons growing up and having a family. I think that's really cool. And like, how do you know when your little electron kid is successful? When it propagates to infinity.
His whole explanation though was basically like based on the rate at which he was cranking the thing, it would amp the flow up to a point where it would overcome the like the dielectric constant or whatever for air and cause like a charge spray. But I was like, well, all he'd have to do to get around that and see if it was true is just crank it really slow and charge it like a trickle charge it,
Mm-hmm.
Because if you just crank it really slow so you never get above that voltage and it still charges and holds a charge, well, your explanation is not an explanation then. But he never did that.
Never did it, dude. And this was causing students sleepless nights, boys, as he said. So. And he pacified them all.
I don't know that many university students that lose sleep over, concepts that they were talking about in physics class. But
well, you know what? That might have been a joke then, right? It's a little dry humor.
Well, I used to lose sleep. I used to stay up really late doing physics.
But it seemed really relevant because it fundamentally violates what they've been taught, right? So they're like,
what's
what?
interesting is a lot of people do teach nowadays though that charge is stored in the insulators.
Yeah, that's cool. I was telling my buddy about that, and he was like, yeah. I was like, oh, that's not a shocking revelation to you? He was like, nope. Like, how did you know? And it's just what it is now. So that's cool. Maybe Mandela effect happened or something. And everyone always knew.
Alan, I just want to say a great marathon presentation.
Thank you, sir. Thanks for helping out with everything too behind the scenes, bro.
Well, I did. All I did was ask some questions.
But you do, you've done more than that. You're always in the back helping out, helping find things.
Well, all right. You're welcome. With regard to what was just being discussed, I think now there's a good reference which you know about already. It's Steinmetz's book, Electric Discharges, Waves, and Impulses, where he does talk about the dielectric field.
Dude, I got to read that.
So, who was speaking just now? I wanted to recommend this book to him.
Pizio, I think.
Oh.
Right?
Yeah.
I think you can get it free.
Dude, Eric doesn't recognize you on a different server. He's like, who is that?
I don't. Well, actually, I had to join just now to listen to this.
Oh, my bad. I thought that was funny.
Well, all right.
Sorry, dude.
That's all right. There's a lot of people in the room, so I was trying to say who was speaking here on the image.
True. And you don't talk to Pizio all day, every day, too. So there's a distinction there, too.
Okay. Well, anyway, I wanted to recommend Steinmetz's book. It's I think you can get it. You can. I think it might be in one of the docs.
Reading night, boys. One new reading night. Are we about the Steinmetz?
I need I need to read that before the fall, or not maybe the whole book, but like I need to go over some Steinmetz stuff for the fall.
Okay, I'm gonna Alan. That's a Piezo. Yeah, this is an excellent idea to read Steinmetz for reading night because I think it would be more productive than reading, Schrodinger.
Yeah. Well, we already read we read a little bit of the lectures already. We get the gist. You have your field instead of single particles. You just add another field and you're good. You go. You just field it up, boys, and you're straight. So that was the answer. So yeah, I think that'd be dope to read that.
Well, the nice thing is Steinmetz. He wrote this. One thing, he really knew electricity. I mean, he knows it better than a lot of professors today. 100 years later, but he knew electricity, and it was before relativity. And I think it was even before the electron, but he still knew electrical properties in and out.
Nice, dude. I can't wait to read it. It's on my wish list or whatever, but other stuff, but yeah, it'll be dope to read that. We're definitely I'm going to put in a word with the boys and see if we can start reading that on Monday.
Yeah. What's it called? Is it the ERP paradox?
Yep. The Einstein, Podolsky, and R. Rosen.
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 EPR, sorry.
Yep.
Yeah, I mean, like, weird that they were able to completely break down the entire behavior and laws around electricity before anyone ever thought of defining it as quantized particles. And then, 50 years later, they decided to try to quantize it. Like, yeah, you just can't possibly measure it. It's just like this, uncertainty principle. And then Einstein and his buddies realized that would completely undermine everything that they'd done. So, like, oh yeah, hold my cigar,
dude. Like, Copenhagen interpretation. You say, 1 second, hold my math, and they just got into a calculator fight, and Einstein won. And then nobody ever talked about it, and it's not referred to. So if anyone starts to get too quantum on you, be like, whoa, have you heard of my boy EPR paradox? Oh, what's that? Well, it's when you take the math from the first wave equation and then just apply the entanglement math to that. And oh my God, you get the solutions for the second wave equation without measuring or disturbing it, and you're good to go. Oh no, but wouldn't that do the thing? Well, no, actually, it wouldn't do anything different in reality because the whole thing is based on just philosophy anyway. They're literally squaring a wave solution, boys.
Yeah, I mean, it's not.
They already solved it with a wave, and then they're squaring it, and they're saying that somewhere in there is a quantized particle of energy. Like, nah, there doesn't have to be though, and then that's it.
It's almost like the act of knowing where it is without measuring it. It's actually it just is where it is.
Dude.
It doesn't
Yeah.
like detect that it's being detected and then take on shape and form in a definite place in reality after it realizes it, as if it's some like, you know, demonic, conscious, like otherworldly, ethereal,
Oh, dude.
multidimensional entity.
It realizes you're trying to measure it, and then it starts hiding from you, so it changes time.
Yeah, that's kind of ridiculous. Was it that woman who did the experiment? Did you say that she thought it was the weight? It was psi that was the probability rather than psi
Yeah.
squared?
Yeah, dude.
The what?
Yeah. So in that video, she comments that the way that she always conceptualized it and taught it and was teaching it was that the wave function is the probability abstract, not real thing, and that the real thing was the particle of it, right? Like the discrete energy packet of the photon. It was like, wow, dude, how did you not realize that you already waved out, and then now you're doing an additional thing just for fun?
Hold on a second. Did somebody say sine squared? Is it wait, because it's sine wave and then you square it and then
Psi.
Oh, I may have maybe
No, you got
did
it.
I say psi or sine?
You said psi.
Okay.
Okay,
Oh, you're talking about the formula for never mind.
Yeah. The Schrodinger's wave equation.
Yep. Yep.
Well, it's kind. Is she a teacher or is just a student or who is she?
She was a teacher. She's a PhD.
Oh.
She's a little she's a little quantum lass. She was like, "Oh, this forever changed how I think about light." She actually just did another video too, like an update. Have to check her out.
An update?
I think so.
But I couldn't teach quantum, but even I know that the psi function is a complex function, and you don't have complex numbers representing probabilities. That's why you have to square it to get a real number.
Yeah, well.
Okay, I'm gonna have to watch her video and see what happened. What's the deal there?
Yeah, I mean, it's just indoctrination, right? Because it's like you said, it's presented one way, but they philosophically look at it backwards, essentially, right? Because that's all Max Born said in his 1926 paper. He's just like, look, boys, we can square this, and then we can say it exists in here, and that's it. Like, there was no experiment, there was no anything. He just philosophically posed it, and then he was like, and if you're down with this, you have to accept that you'll never be able to measure any of these particles. And if you're cool with that, you know, you're down, you know, we can rep the same set. And then Heisenberg came in and was like, oh, dude, I got you on that Heisenberg uncertainty principle. I was trying to measure an electron myself with a gamma ray microscope. And wouldn't you know it, the little photons were playing billiard balls with the electrons, and they were knocking them out of the way. So it turns out you can never actually measure them. The more precisely
it's like the photon that I use to observe it, because that's what light is. You know, that's what we see. The actual thing that I'm using to look at it is knocking it out of the way, so I can't see it.
This other abstraction that hasn't been verified in any meaningful way is preventing me from measuring this other abstraction that hasn't been measured in any meaningful way. And the reason that we could never physically measure it in any sort of meaningful way is because the two abstractions are abstracting together in a cohesive way that's predicted by my abstraction, which can't be falsified or anything. So
they cancel each other out, maybe. Oh, Alan, before, who was it that you just said that you quoted? He said, you have to accept this. Was that Born?
Yeah, that was Born, and Heisenberg has his own rendition of that too, which I don't know off the top of my head.
You know,
but he has his own thing though. What's up?
An electron. What did they say an electron would be? Like a one terminal end of a uniline of dielectric conduction. Hold up. If you take the wave equation and you square it, physically, aren't they basically just take like think about take your hand, do like the wiggly squiggly wave with your hand,
right?
Just imagine imagine your fingertip as the front end of the wave.
Okay.
When they square it, they're basically trying to tell where the tip of that wave is at one exact point in time.
Okay. Makes sense.
Or the center of mass or the tail or any specific part of the waveform that they measure from, whatever phase of the wave they want to measure, right? But
Yeah.
that's what they're trying to quantize as a particle. There's not actually a particle there, though. That's the reason they can't find it.
Right. There's a good question. What is it's all right. It's a solution of an equation that looks like a wave equation. Well, I have to say his name, Schrodinger. I'm trying to minimize now using his name. Anyway, that's another thing.
You're good. You could say the vicious pedophile Schrodinger every time you say it, just to put it on blast.
That's yeah. And well, anyway, I know that's going to shock a lot of people who haven't heard that before. But anyway, it's sort of like the Schrodinger equation is like a wave equation. So again, a wave is something is waving. However, the wave equation is only a mathematical function that describes information about a particle or a system. So the question is, what's waving? It's not the particle. It's not actually the probability, because you have to square it to get the probability. So, you know what? This might be a very interesting thing to look into. Has anyone interpreted exactly what is the psi function?
Dude, you're so spot on, Eric. It's insane. My boy, It's BS I'll have to look it up on his Twitter thing. But yeah, exactly. What is waving? All of these equations are describing the exact same thing. Perturbations in a medium, bro. And he has all of the backwards derivations for it because it's always ever been this, right? It's crazy.
Yeah, that's what Schrodinger wrote a little bit of stuff. Like when they came out with this whole quantum garbage, he like responded a little bit to it and was like,
he hated it. He thought it was retarded.
Yeah, he was like, these equations were never meant to be used for this purpose. Like,
dude,
they were meant to describe like physical reality.
That vicious pedophile was so upset that Max Born bastardized his equation by squaring it so he could roleplay a probability function for his electron stuff so they could play billiard balls together. He was so upset by that he did a 4-part lecture series where he turned the electron, right? Dude, this is how you know you pissed off someone, when they take your billiard ball and just turn it into a field and then completely eliminate any need for any billiard ball interaction with said billiard ball. Just erased it, dog. Mathematically, just like seeing that was very eye-opening, because it's just like, oh, none of this is mutually exclusive or meaningful. This is a battle for how many people I can get to believe in it.
Well, to make it accepted.
Yeah.
I believe there's a quote by Schrodinger where he didn't like the way quantum mechanics was going, and he said literally, I was sorry to have anything to do with it.
Yeah, dude, Dirac said similar stuff. Dyson Freeman said he thanked Fermi for going, hey man, you don't realize you're drinking the Kool-Aid, bro? You're using all the free parameters to make your math match the measurements. And he was like, oh, you're right. My bad. And thanks. I almost went down a blind alley, dude. What's a blind alley? It doesn't sound like a path to enlightenment, to understanding physical reality in a meaningful way. It sounds like wandering around in the dark, not knowing anything.
You talking about when they used a power series and started applying a fourth and even a fifth coefficient in term in order to like shape the curve exactly the way they wanted it to be shaped?
Yep.
Right. There's a YouTube video clip where Dyson is actually telling the story when he went to Fermi.
It's phenomenal. Oh, no way. He has the Fermi story too. I seen one. Well, actually I played it for the thing, but it's where he's saying, where he came up with the idea for the refutation, where if you apply it on an inverse system where the electrons attract instead of repel, that everything diverges no matter what. And it shouldn't do that if the equations if what they were doing was meaningful, in the sense that it was going to output a physically meaningful interpretation of reality and not just cooking the books.
Right. They started adding so many terms. You get to that fourth and fifth term with a coefficient on it. It's like,
Dude,
what do each of these terms and coefficients represent in physical reality? What is the thing, the object that's causing this term and coefficient to appear in my equation? They ran out of stuff after like the first and second.
yeah, dude, they're up to like 12th order corrections. So it's very fascinating.
Oh, they're way beyond 12th order. The Feynman diagrams can go on and on and on. I'm gonna go on mute. I'm gonna find where Dyson tells the Fermi story, and then I'll give you the link, Alan.
Dude, awesome. Yeah, if you're able to stream it, if you know how to do that, if you could live stream it for us, we could watch that real quick. Because yeah, we read a little bit of the interview, so that would be nice to see it in context or to have him tell it.
What I'll do, I don't know how to do that. It would take me too long and time. I think.
No worries.
What I'll do, I think I can find it quickly, and what I'll do is I'll post a link to you and then you can stream it.
Okay. I'll see if I can have that arranged. Riggs, are you here, my boy? Riggs, my boy. Yeah, he's here.
Yeah, I just woke up, dog. Just woke up.
So when Eric, when Eric links this, will you swoop up that link and stream it?
Will I what now?
Eric's gonna link something, a YouTube video. Will you stream it for everyone?
Yeah, I got you.
Thank you, sir. Can't stream audio at the moment. I got to do some reconfiguring of the old system.
True.
Yeah, so what were we talking about right before that?
Particles are fake and gay.
Yes.
Virtual particles.
Virtual particles, fake and gay. So yeah, you'll see stuff like, oh, dude, we measured the magnetic dipole anomalous moment of this, and therefore the
T2 factor.
Therefore the annihilation positron pair, like all this stuff, right? Okay, what did they do, guys? They induced a magnetic field, and they measured it, and they used a bunch of math to predict or post-dict how strong that magnetic field should be. And that's it.
You know what's wild? They claim that they have like opposite particle pairs that can collide and self-annihilate with each other. And cease to exist, just oblivion, right?
Mm-hmm.
But how do you describe that in terms of a wave? Well, dude, I mean, when a peak and a trough meet, they cancel out. They have that destructive interference, and they go to the zero in the middle.
Nice.
I mean, if I've got the zero line as neutral, the top of it's positive, the bottom's negative. If I've got equal magnitude on top and bottom, and I make them hit at the same time, there's your annihilation, bro.
Nice. All right, we're going to watch this video real quick and then remind me to talk about the information paradox, right? Because we're going to get into a situation where it gets a little precarious with the annihilation of the virtual particles, right? Because we'll break down the information paradox, because that's a hilarious one that's supposed to reify relativity theory and black holes. So here we go with the Dyson thing that Eric put up. So while this is playing, I'm going to take a quick break, and I'll be back.
We got everything cooking?
Yep, go ahead. Ready when you are, sir.
Let's do it.
I go and show these results to Fermi and tell him how well we were doing. And we wanted to have Fermi's blessing on our efforts, as he was the prime mover in this whole subject. And it was a good opportunity for me to get to know Fermi. So anyway, I arranged through Hans Bethe to go to Chicago and tell him about what we've been doing. And so I arrived at Chicago and knocked on Fermi's door, and he was very polite. I came in and he said yes, and I showed him the graphs on which our theoretical numbers were plotted and Fermi's experimental numbers were plotted, and the agreement was on the whole pretty good. And so Fermi hardly looked at these graphs. He just put them on the desk, just glanced at them very briefly, and he said, I'm not very impressed with what you've been doing. And he said, when one does a theoretical calculation, you know, there are two ways of doing it. Either you should have a clear physical model in mind, or you should have a rigorous mathematical basis. You have neither. So that was it. In about 2 sentences, he disposed of the whole subject. Well, then I asked him, well, what does he think about the numerical agreement? And he said, how many parameters did you use for the fit? And how many free parameters are there in your method? So I counted up. It turned out there were 4. And he said, you know, Johnny von Neumann always used to say, with 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. So I don't find the numerical agreement very impressive either. So I said, well, thank you very much for your help, and I said goodbye. There was nothing more to be said. So the whole discussion took maybe 10 or 15 minutes. So I came back to Cornell to tell the team the bad news. So that was another watershed in my life. And I think it was profoundly useful what Fermi did. He had this amazing intuition. He could spot what was good and what was bad right away. I mean, we might have worked on these calculations for 5 years if Fermi hadn't given us the red light. And
dude,
as it was,
right?
Fermi,
dude, that's insane. He's literally like, hey, he's like literally what you're doing has no meaning or value. And he was like, oh, dude, you're right. I'm going to dip and do a different line of work now. This is the father of QED, boys. So if anyone says, oh, you don't understand it. You didn't, where'd you get your, where's your no, boys, the guys that made it all dipped.
And dude was like, oh yeah, if you hadn't told me that, I might have been over here playing make-believe and pretend for the next 5 years.
That's literally what he just said. Please continue.
Fermi was absolutely right, because in the end, of course, it turned out the theory on which we based the whole calculation was an illusion. There is really no such thing as a pseudoscalar theory of pions. That in reality,
no way.
10
that
years
sucks.
later, or whenever it was, quarks were invented. And the whole theory of the strong interactions was totally transformed into a theory of quarks. And it's only when you represent the pion as a compound system of 2 quarks that you can begin to have a real physical theory. So our whole physical basis was wrong. So it was perfectly true that any experimental agreement we found was illusory. But it took Fermi to see that.
Pause for a second.
He could see it without knowing about quarks. Of course, nobody had dreamed of quarks at that time. But he felt in his bones that this theory was no good. And he was right. So he saved us maybe 5 years of blind work. And so I'm extremely grateful to him for that. But it was a tough situation for us, especially because we had some graduate students involved in this project. They depended on it for their PhD thesis. So it was difficult. I mean, I simply had to tell the team, look, I'm sorry, but this is not going anywhere. So all we can do is write up what we've done and publish it. But it's not going to go any further. And you better find some other line of work. And so it was not a very pleasant experience for the graduate students or for me. But in the end, of course, it was for the good of us all. But that's the kind of genius that Fermi had. And I think that showed me very clearly that I wasn't a particle physicist, that I didn't have that kind of instincts. I mean, my gifts are in mathematics and not basically in physics. So I can, when there's a theory that is well based on physics, as it was in the case of quantum electrodynamics, then I can do marvelously well with using it. But I'm not able to invent a new theory. And what was required for the strong interactions was an invention. And that clearly wasn't my cup of tea. And so from that time on, I didn't seriously try to solve the problem of strong interactions. From that time on, I worked in field theory on the mathematical side, and which I could do very happily and even usefully. So from that time on, I was interested in the mathematics of field theory, and I got involved in the Whiteman program of trying to establish quantum field theory axiomatically and deducing from axioms physical consequences. That's something that I love to do, which is, in Fermi's terminology, that's based on a firm mathematical basis. Whether it's physically correct or not, it's certainly mathematically sound. So I made that choice that I would go with the mathematics and not with the physics.
Well, there you have it, boys. They passed the buck off to a new invention, the quarks to explain the interactions that they couldn't, and it still suffers from the exact same problems. They can't solve any Feynman diagrams without renormalizations that diverge to infinity anyways. Unlucky. Thank you, Riggs.
Are you whispering, Alan? It's hard to hear you.
Shoot. No, can you hear me now?
Yeah, you sound better now.
Okay, I was kind of away from my microphone. That's my bad.
I heard you fine the whole time, bro.
Oh, shoot. Okay. I don't know. I don't know what to say then. I'm at a loss of words.
No, you sounded fine. I'm saying you sounded fine.
Oh, I did have my head turned, so maybe it was that. I don't know. But doesn't matter. Who solved quantum electrodynamics? Wonder what that video is about, boys. Oh, we all just lived it. Okay.
Right, that was yours. Hey, who left a comment under my posting? Says, "Here comes the gaslighting." What gaslighting? From the Globers?
I don't know. Never met her.
I don't. Is that at me or?
I don't know.
I'm trying to be useful.
Yeah, you got to be careful with reading text chat, man. It's a vicious in there. My boy Eli's in there right now fighting, I think.
Oh, okay. I'm here. I don't want to argue with anyone. I want to be helpful.
Yeah, dude. Eric's a librarian, boys. He's not a Glover. All right. Let's see here. I think, cool, man. So we've done a good 4 hours and 15 minutes. I think we've sufficiently covered it. If there's no further questions, comments, or anything like that, I think we can wrap it up. Gio, thank you so much for hosting this, man. Much appreciated. It was awesome to come through and do this event here.
A lot of.
Yeah, for sure, bro. No, that was definitely a lot of information, and yeah, good work, man. It's good to go through a lot of this stuff, and yeah, that's one to perhaps go back and go over more because yeah, there's a lot of information in there. So yeah, cheers.
Cool. All right, I'm going to go ahead Riggs, you can end stream if you want. I'm going to go ahead and end my stream. I'll be back in a few minutes. All right, where's the YouTube chat button at, boys? Where are the boys at? Thanks everyone who hung in there for the whole 4 hours. It was quite a ride. I know it was a lot of information, and some of it was, probably a repeat, right, for those who have watched the first one. But it's good to do it in repetition and learn it. So anyway, thanks for tuning in, and let's see what we got coming up on Sunday. I'm going to see if we can do a reading night for Bring Your Own Brenner Comp. And then Monday we'll be reading, hopefully we'll be reading a little Steinmetz, but if not, we'll definitely touch back on the art book from our boy Halton Arp. And then Tuesday, Dr. Bennett will be presenting his Ether Hildegrad model. Again, we'll be getting part 2 on that. So if you guys had any questions or wanted follow-ups, make sure you send in an email to AlanSpaceAudits@gmail.com with the title Bennett Prez or Prezi, something related to presentations, and post your question there and we'll get it answered for you. Or stop by on Tuesday. All right. Thanks. Bye.